University, Puttaparthi, India in 1999 and 2001 respectively. He also obtained a MSc degree in engineering from Indian Institute of Science, Bangalore, India in 2004. He received a PhD working as a US Department of Defense Breast Cancer pre-doctoral fellow in biomedical computation from Dartmouth College, Hanover, USA in 2007. He worked as a postdoctoral research associate in the Department of Radiation Oncology, School of Medicine, Washington University in St. Louis, USA from 2007 to 2008. Currently, he is working as a professor in the Department of Computational and Data Sciences, Indian Institute of Science, Bangalore, India. He is going to deliver a talk on mobile-friendly deep learning algorithms for medical image analysis. We are truly delighted with your presence, sir. I request you to kindly hand over the session.
Thank you. Thanks for this introduction. So what I'm going to do is I have divided my talk into two parts. So the first talk is going to be on deep learning. The second talk is going to be on the little bit more about what is the future of the deep learning or artificial magic, and also a little bit analogy to autonomous vector detectors, where we are getting in terms of vector analysis. So with this, again, Mr. Thank you for the nice introduction. Thanks to Mika and thanks to Mr. Mohan for having me here. So before I go, I have a few conflicts of interest. I work with a lot of companies. There are a few companies I received funding from either directly from my directly as a consultant or some of them. So these are standard ones. Again, the work which I'm going to present has a large collaboration effort from Mr. Megarity and Amin has come. So thanks to both of them who are contributed majorly part of the work which I present. So just get into the outline of the work. I just want to introduce medical imaging because I thought that people may not be aware of it. And then I talk about AI in radiology, and then I talk about what is the need for mobile-friendly deep learning algorithms. Then even though I have come as our own lab work, as I said, it is being contributed here as well, where I talk about management of the COVID-19 in terms of the carbon pandemic which we are doing here. So let me just get started on the medical imaging part. The way we introduce medical imaging is that the broad definition of imaging is that it's a visualization of the lesion or the disease. So you want to visualize the lesion or the disease. And then there's something called as radiological interpretation happens after the visualization. And then with that interpretation, you rule out the analysis. For example, the suspicion is that somebody is having a cancer. So then you say that somebody has a cancer or doesn't have a cancer. So we acquire the images on one side, and then we have this radiological interpretation which is being done by the radiologists. Then we have the computing and analysis which people like me do, which essentially makes the physicians have the data more useful for the clinicians for the interpretation. And if at all you think about it, AI plays a role in this computing and analysis, including part of the application. So we want to make the radiologist interpretation a little more easier. So again, there are many imaging modalities that exist in the current things because each one of them provide unique information, physiology or morphology or metabolism. For example, if you are thinking about computer tomography, which is mainly X-ray driven, it's mainly covers morphology, which means that you will be able to give you structures very well. To some extent, it will be able to do physiology information, which is four-dimensional scans. But then if you are looking at nuclear medicine, to be able to give you more information about metabolism and molecular, which is more of a physiological. So in very simple sense, if at all you are interested in detecting cancer at every stages, you got to think about utilization of nuclear medicine and flow cells. And if at all you are thinking about more than stage 2, then you are thinking about looking at CT ultrasound, very simple sense. So with that small introduction, I'll get into the AI and radiology. I'll come back to this topic of where does the AI in this kind of realm of things. Before I go further, I'd like to just precisely I want to define the medical imaging more. We interchangeably use AI, machine learning, and deep learning. So to just to clarify that, we think AI is a big component of this, which is super sad. And machine learning is part of the AI thing. And deep learning again is part of the machine learning. So we think AI is a superset, and machine learning is one subset. But that's deep learning exists. And all of that exists because the reason is that we are interested in doing this is in the space of the digital health, where we want to make the healthcare more and more digital. We want to go to digital transformation. We would like to do precision medicine, drug discovery, imaging and pathology, including the patient data management. So these are all part of the topics of the AI which happens in the healthcare. Now, why does the medical imaging plays a bigger role? The reason is very simple. But I think healthcare is generated a lot of data. 90% of the data is imaging. So that means that if you talk about analytics, 90% of the analysis has to be on imaging. That's why it's very important for us to look at this, that 90% of the data being medical images, and then we want to analyze this. And this is something which is we call it as value chain. So that when data is the value for the analysis, what can analysis, actually do? So now at the bottom of the things you have the data, which I said 90% of the data is images. And then on top of it, we can do what is called the screening. So when we say we are answering the question, some of these have the answer has to be yes, sir. This is a binary question. So the answer is yes, sir. It's a binary thing. How to say yes. That is not the screening. If you really ask what is the value associated with such a answer, how much of a patient is willing to pay for that, that will be around 10 or. But if you go further and make it a little more precise, we call this over diagnosis, saying that somebody's having cancer, they are having a grade 4 cancer. So now we are bringing the precision into the diagnosis. So that is roughly the cost of the diagnosis, which is 3 times more than the screening. Then we go further, which is the ultimate pinnacle. The action, which we call the stream. What kind of people is better suited for such a candidate? So that is where the real realm of things is. So where somebody will be willing to pay hundreds of dollars. Now, where we are in terms of AI, we are between somewhere between screening and diagnosis. We are not in terms of how much clinical, but we are somewhere between screening and diagnosis when we are talking about it. So whatever I'm going to talk about is mostly to do with the diagnosis. That's what weighted I talk about. Now there are these such medical imaging has something what we call as needs. So what should be done? So we divide this into what is called as clinical needs and science needs. So that means as a surface what we are expecting in return. So there are many needs. I won't go into that, but I'll just say that one of the things which I would like to emphasize is that when we talk about clinical imaging, we talk about faster imaging, cheaper, less radiation, screening, global level application. And we're also talking about radiation. Right, and then other things which clinic also wants, for example, like email imaging is something which correlates as to show in the science. You want to look at that imaging as well. You want to look at therapeutics and biology combined with imaging as a part of the clinical need. But the first two parts, which is faster, cheaper, less radiation, screening, global, and retention, is where AI is a bigger. So that is where AI has a really in terms of meeting those needs. So, and again, this is not only about screening, not only about diagnosis. There are certain operations which AI can also help in terms of argument. For example, like, think about, we talk about recommending the treatment, which is argument. But we can talk about optimizing the operation processes. So, for example, does the patient needs to be scanned for 3 minutes? So, we have a standard protocol where we scan something for 60 minutes. Why not in 1 minute? It doesn't require same amount of common stage. So, they are not part of the operation. So, you are increasing the throughput of the scan, probably the distance based on more information streams. And then we can also talk about recording the digital medical notes. We all this, at least to a certain extent, thanks to mobile phones, we can see the Alexa, use Google to a certain extent. So now, why not do the recording of the digital medical notes? Why not? Now again, also we are talking about supporting the population health management. So it's becoming a critical issue where population health is required to be looked at different ways. And again, we are talking about monitoring, guiding, and health trajectories, and the part of the So, before I go further, let me stop. So, as it's been, we used to be very proud of publishing not just one things. As a field, as an area, medical imaging is to publish one of the largest papers, right? So now what we think about, like, roughly the number of papers which will be published is, I'm talking about when I did the PhD, which is around 2005. Very problem, but we are a large community which are using quite a bit of papers. And fortunately, unfortunately, machine learning came over thanks to general purpose GPU, which has ensured that integrity deep learning and other things. Post 2010, when the GPU became more or less standard practice and became growing. So today, as an area, machine learning functions more existence. Right? So now, if you think about the papers it is publishing, so it about 7,000, 8,000 papers. It's just not machine learning, it has a single area. So this is a problem we have in terms of, so anybody who tells you that we only summarize machine learning in 3 days workshop, I could just laugh at them because the number of papers that are getting produced is really enormous. So this is, and naturally, right? So now that means that there is a need for natural marriage between machine learning and imaging, because the reason is both of them are very emerging areas, they produce largest number of papers. And so now coming back to this, why does the machine learning bring into the radiology? So medical imaging in general. So we call this our work. So we make the data goes through the clinic. This is part of the work. So we start from the acquisition, I told you, and then we do some processing. Then we form the images, and then ultimately this gets interpreted, and then the interpretation is what made into the report. The interpretation in terms of these image-based tasks. So these image-based tasks are, we divide this into 3 parts again. The first part is the detection, like I told you. The screening is the detection. You answer the question yes or no, whether there is an abnormal tissue present. So this is a little more easier because the reason is that we are only asking whether there is an abnormal tissue among images. Then the next part is, I mean, if I want a little bit better, we want characters. Now we are talking about grading. Okay, there is an abnormal tissue, what grade is it? Or what kind of so that the third part is monitoring. So we are before the treatment, after the treatment. So you are looking at characteristics. So now you can imagine that characterization is little harder than detection. Monitoring is little harder than characterization. So now the problem we have is each one of them requires us to look at the images carefully, look at even for detections. For example, I'm just giving an example of high resolution CT of the chest. High resolution CT of the chest generates 160 images. This is 160 slices of the lung. Now, if somebody has to look about the lung tissue in the 160 images, it's going to be harder, right? Imagine reading through 160 images. That's going to take at least half an hour even to do detection. Forget about characterization. That is even more time. But we monitoring how to get probably like such big sequences. So that's even more hard. So this is what brings us to where the AI can play a role, right? So we talk about these are patterns in tasks that takes after a couple of hours. And then we also have problems in terms of complex protocols. The immediate position itself changes because the technology is changing. The way the standards are beginning to change. So everything is becoming more and more complex. And then today we don't do anything but like HRC. HRC is one of the we don't even do one we combine something with them and all impact. So this is not becomes an issue for us in terms of multimodal information. So this is where they have started playing the role. This was existing for a lot of time. So initially it was on machine learning, where what we were doing is we were doing the picture engineering. So that means that people like us who understand the image intercepts, we call ourselves experts. We will say that the abnormal tissue can be recognized by looking at texture. Our abnormal tissue can be recognized by looking at histogram, which is essentially texture. Our abnormal tissue can be recognized by history. We choose the picture which we want to select. We select that picture, and based on the picture, we do the classification. whether it is a one or all. So this is what was traditionally machine learning was doing. This classification was done by the machine learning algorithm like SVM. It's one example there, which was really good. Now the deep learning became, you don't need to do any feature things, so that people like us making you don't require knowledge. All you require is good amount of computing power. Here we are to decode the images in terms of sense use the neural network. And then, the feature is learned or shown by using the neural network, ultimately increasing the prediction of the data. Of course, the disadvantage here is that we require a lot more data compared to here, which was standard machine learning was working. Standard machine learning one can work with less number of points, but whereas the deep learning require more data. So this is what has brought us to feature extraction, machine learning classifying and prediction. Deep learning doesn't require us. One of the problems also we had with feature extraction was that it was not reversible. When the protocol changed, probably the feature had to be changed. And of course, the same problem is there, but it was to a not expert in this. So now again, either one of these, either traditional machine learning or deep learning, they are all task dependent. And at least the traditional machine learning requires understanding of the imaging physics and clinical knowledge to choose that culture. Whereas with deep learning, all it requires active data being present. You don't require to have the knowledge. All you know is GBG. That's the main thing. So now, even though I said, I don't talk about what are the challenges currently that exist in terms of these AI models, the deep learning models being present. But again, I don't have any solutions for this, neither proposing any of those. Then each one of the questions I'm putting up is a big area by yourself. That means that there are people who work in this answering this one question, which I'm putting out here. So again, as I said, there is a data exists, and we are trying to either develop a deep learning model or a machine learning model. Then ultimately we are getting some solution. So now I have divided the questions into each one of them, right? So the first one is start from the data. So if at all you want to develop AI, how many images will you get? So that's the first question. So now again, you have an answer. Yes. So there's a difference between having an answer and having an answer. So now that again, this becomes more or less subjective. How many images do you get? The second question is, okay, we said that you require 1,000 images. So what happens if I don't have 1,000 images? What happens if I don't have those images data? Because I might be the person who's working on a day basis. 1,000 images might not exist. You don't have that. So now, yes, you have an opinion. But the answer, the next question is, what happens if I don't have enough opinion? I want 1,000 images, which I want. I don't have an expert who will go and annotate the data and give me the what will be the answers. So again, there are methods which can answer this, right? So for example, the question to answer the second one is what if you don't have enough data? Probably you can use some documentation. Augmentation of the data for the deep learning itself is the big area. The third question is you can do some amount of supervisor or semi-supervisor. Again, unsupervised and supervised methods are also a big area. And then again, come to the bottom, right, which is the middle part, right? So, do we really need deep learning? The second, do we really need deep learning to apply every problem that is out there, right? The question that's a big question. Is there any off-the-shelf models? Is there anything which I can take it and use it in the metro? From which is coming from computer vision, which is coming from other ones. So now most of the diagnosis, which is the prediction we are talking about, the clinicians will always look at it in the context, that is the patient history. They consult with other clinicians and then make the diagnosis of the prediction. So now how do you come with that kind of context of prior into the models, which are the independent ones, which are fully data driven, but they are all independent. So how do we apply it? The next question is there more kind of friendly or user friendly? So can I make something which is very friendly or user friendly? That is what our happens. So we work on developing friendly and user friendly. And then in terms of result interpretation, can we visually interpret the result? can be applied in human clinical interpretation. This is all part of the experiment, which I talked about in the second part, yeah, in the class of other things. So now again, I'll just answer a few things on the deep models. So the reason why you want to answer the very deep models is that it has to be better than humans. So for example, you must get character. So what you want in the morning versus what you want in the evening is different. So humans also need to take a rest. They also need to sleep. Whereas machines doesn't need to do that. Machines are tireless and you can move them. So that's one way of looking at it, that you remove the variability which naturally comes from humans. And the other question to ask is that, especially in deep learning knowledge, machine learning algorithms are able to give good predictions. Deep learning will be able to improve the performance. And now the question is, do you really require that performance or not? If your machine learning algorithms are what we call as non-deep learning algorithms are giving you performance from my interface. So you may not know, but if they're only giving you 70% performance, if you want to improve the performance, then you require deep. Off-the-shelf models, this is especially for the students. So anybody who is getting into the medical image analysis, if you want to do biomedical image segmentation, the first one as a baseline we apply is what is known as UNIT. So UNIT is what gets applied. It works with very small amount of images, around 300 images is what you require to train them. The next one is if you are doing 3D image segmentation, we call it as VNet, which is essentially a resident type, or it's called ResNext. If you learn the resident function, it's an expansion of VNet. Important. And if you are working on with a lot of variability, so for example, like skin cancer, histopathology, fungus images, they all have different scans. They all have different exposures. They all have different stages. So there's a lot of variability in the data. So if there's a lot of variability in the data, then I would say that any of the inception networks, which have some state connections and other state connections, are good ones for some manipulations. So these are all the networks which you can apply as basic ones. So now this brings us to, this is what comes to the next one of this topic. So before I go further, right? So whenever I transform image analysis, there are a couple of things that have come very important in the past, at least the last 5 years. So the first one is what we call as point of view imaging. So very simply to put it, what is this mean is that today when people come walking to the hospital, walking to the diagnosis, they want to get the diagnosis done. They don't want to be referred saying that you go and get a scan, experience, and then come back. That's delaying the full diagnosis. So point of care diagnosis means that you do direct diagnosis. For example, the best example is OBGYN. So when you go for a gynecologist, especially the ones who are pregnant women, now today it is a very common one where the gynecologist is having an ultrasound machine in the office. Earlier it used to happen that they used to say go for the ultrasound scan, which is right next to it, and then you go for that, wait for it to get the scan, and then come back. Today, every gynecologist uses a point of care ultrasound machine, which is very easy. The same thing is cardiologist. They using ultrasound. And then that also means that it has to work at the bedside. So this is part of bedside medicine. So this is looking at the consultation bed on the bed in the hospital. That means that we are talking about miniaturized and specialized imaging devices. That is also on the device. And then most of the need-based tasks, I will take this involve only 34 classes. I just want to bring an analogy to what happens in the computer vision systems. Autonomous systems are computer vision. You are looking at probably thousands of classes. Because what you see on the road is thousands of classes. Whereas when you talk about the tumor, we are talking about going from grade 1 to grade 5. So we are only talking about only a limited number of classes. Compared to one, of course, this is specialized, there is not variation in the data, but at the same time, there are only 3 to 4 classes. And what we call it as AI workforce being closer to source. So one of the problems we have in terms of image acquisition is that if at all there is an artifact that has come into the images, there is very little we could do. We can't apply AI on that because the reason is that the data interface is having corruption analysis. So now, in some sense, we want to bring that closer to the source, and such that we can tell the domain experts that then they need to choose whether this is a good data for AI. And then, most importantly, right, so there is something which is happening. Those of you who are very dedicated to healthcare, most of the hospitals run by the surgeons. Surgeons are the critical part of the hospital. But they are the ones who run it. And integrated surgery is one of the most important things for everybody to do. Because surgeons run it, and surgeons are the ones which do a lot of imaging. So AI code processing, if at all you think that it has to help the search, then you are not going to have an latency. So that means the AI will not take forever to give the result. So because they are doing the surgery, that will be quite feedback. So now this is what brings us to what is called as edge computing. That's an ideal case for edge computing. And then again, this is common across multiple systems, autonomous systems, and edge computing. So we say that there are 5 advantages with edge computing. One is it's a cost factor. Anything which is put on the edge, we are going to have very cost. And then you have a proper coding between the legal and modern devices. There is obviously if you have to latency because it's a very fast response for the applying on the machine. And then of course, you don't require connectivity at all. Because that's a whole premise of doing edge computing. It's a very reliable operations. And there's a security and compliance. So when we talk about the edge devices on the deep cloud, we typically talk about deployment. So for example, if we want to apply the deep learning algorithms, we require to use at least in world where we do 3D imaging. We require to use something known as A6000 cards, which has 48 GB memory. So if at all you buy one of them, which is A6000 cards, that will cost you roughly $150,000. Now compare that with something like NVIDIA. That costs you roughly, or even the higher end cost you roughly $700 to $1,000, which is 15 times less. And more importantly, this doesn't occupy as much footprint as these big cards. So if you are thinking about hospital, nobody would like to have this big machines lying there, right? And then you can't carry it everywhere. Like I just spoke about doing it on the bedside, doing it on the bedside as well. Of course, I talked about all the fast inference, easy deployment on mobile devices. I'm showing a couple of examples, and as well as embedded platforms. Not only Jetson itself is very embedded for inference, but then you can also talk about going to Raspberry Pi, which is even more, like machines. Of course, while we are doing it, as I said, all these things we have to do. So now, again, if I have to teach you, I will teach you about 10 hours of this, because each one of them is a big field by itself. So, for example, you can do this by something like what is known as low-rank approximation, where you project onto the common sense. You try to make it as a low-rank approximation. You can also do something known as network quantization. This is what typically we use. And then there is something called as teacher-student model. So again, that's a big area by itself. And then you can also do network pruning, where you try to introduce a number of connections between the layers. Then you look at embedded connections and then do that as well. So again, each one of them has its own advantages, disadvantages, as methods which are applicable everywhere. But what I will talk about is that I will talk about a little bit about network quantization, which we have used previously. And then I will also say that you can also design the network keeping in mind that you are going to develop it for time. So again, if at all you want to do the deep learning in the edge, we call this as 3Ds. So you want to design keeping that you are going to use it in the edge machine, and you want to develop also keeping in mind that it is edge one, and then you also want to employ it on the edge. Now, if at all you think about it, there are multiple steps, but there is a data pre-processing all of us have to do in terms of deep learning models. And then what you do is that you design the model in such a way that keeping the edge device in mind, and you also do training and validations. So that's the other the step 3 where we use something like TensorFlow Lite and PyTorch Mobile, what they are doing is that they are doing network quantization. So in very simple sense, instead of using double question, they are using single question, right? And instead of using single question, they are only using 4 bits. Single question requires 8 bits. So in that way, that what you are doing is the range which you are putting there. Now the amount of memory required is going to go down heavily because instead of using double, you have come to single. That means from almost half of the memory has been reduced. The model itself now occupies half of the memory. So that means that it's easily deployable on mobile. So now again, there are platforms which are available which will do this automatically. That means that you give a different model, which is a TensorFlow model, and they will give you like a question which you can deploy. And of course, you deploy to a device. It doesn't mean that the TensorFlow Lite can easily be deployable in Android and iOS and Raspberry Pi. You might have to string design part to do it better, but still, it will give you some amount of flexibility for you to do this. Now, what are the examples of the like you've seen that there are many which are available. Most of you doesn't know the mobile executive is one of the famous ones, which is that. I spoke about Inception as a one-way model. And then there are some products, there are efficient nets which are also there. Efficient net is a scalable model where you have V1, V2, V4, V6, things like that. So now that brings us to our work, which is built on this library for a problem. So let me define the problem first and then we will go on. So this is a case of the code library and then where the HRCT, which is high resolution CT, is taken by a patient. So the patient became a positive for the COVID-19. And I would like you to concentrate on this red box, which is there in each image. So what happens is that as COVID develops, as COVID, symptoms come in, what happens is that the infection in the lung starts increasing. So this, we call it as COVID anomaly. This starts increasing in the lung. So now the anomalies could be the body parts, ground elasticities, there is consolidation, there is pleural infection. And now somebody who recovers, what happens is that, this is after a month from that, these anomalies, the infection starts going away and they become completely normal within a few weeks. So somebody who doesn't recover, now the infection rate is going to occupy 7%. So what is happening during COVID-19? The doctors who came to us said that they have this problem of choosing who's the right candidate for the ICU. And beds were not available. Now the question is that where do you choose? Where do you put the person in the hospital, the ICU or not? To know whether somebody has to be put in ICU or not, you need to know how much infection is there. So this is what has brought us to the management of the project. So that means that we want to score this. So we want to say that how much infection is there in CT lung. So if there is no infection, it's normal. If it is 24% of the lung is infected, then we call this mild. Now, anything below 50% is moderate, between 50 and 75 is severe. Anything above 75 is extreme. Now, I think you would have already imagined this is also known as thorax. Anybody who is having this should be immediately admitted to the ICU because there's something of the lung is infected. Now they require thorax. Anybody between 50 and 75 with oxygen stand. So essentially, what our aim was that we need to develop a model which will essentially give this score in our automated fashion, such that we can decide who should be admitted in the ICU, who should be having oxygen, who should not be admitted as well. So what we wanted to do was that we wanted to take an input CT space, which is the lung image. We want to extract the lung, and we wanted to apply a network which we call it as the lung network. And then we wanted to get disseminated abnormalities, which will give the percentage of the infection, which is given by this. So for this, we designed what is called as a block. So where we essentially do one by one for the convolution for the demonstration, is also known as bottleneck. And then we also do 3 by 3 convolution at the same depth. And then again, we do the stretching. So we do squeezing and stretching. So we do both of these operations. because the reason is that we regularize the solution data. So in very simple sense. And then you have the output of the one which is kind of input to the log. And the last function which should be used is what is known as weighted cross productivity. Essentially, for this problem, we have three labels. One is the what we call is known as normal log. The third one is inverted. So for each one of them, we want to weight it such that by each label, such that we give equal weightage to all of them in terms of getting the predictions. Now, the amount of data we have used is roughly about 70 patient data, and these were all put in the public domain. And then, as I told, the baseline for any biological image segmentation, we want to compare it with the UNet. UNet is the baseline model which we have, which we consider as equal strength. And this is our model. So I just wanted to look at the number of parameters. UNet has about 31 million parameters. Ours has about roughly 8 times less. And then I also wanted to think about the models. This is having almost 120 MB, whereas we are occupying at. And then in terms of training time, the training time it was taking around by an hour. We were able to do it in about 30 minutes, roughly half an hour. And even inference, when we are doing it, said that the latency is one of the biggest issues for us. So we don't want to wait for this much time even on the GPU. So this is roughly half a second. Like I was even though we were able to do all that, I also want to think about the in terms of accuracy also. We were quite good accuracy as any of the UNet models which have, even though our model is much more. And then again, I will not get into this, and I'll just say that the predictions for matching what the experts have. Now, this is where people like the help us, because the reason is, can we get all this? But can we really deploy on the edge devices? So we want to deploy it on Raspberry Pi, because Raspberry Pi has very much footprint in terms of resources, and that is what is the lightest edge device you can get. So if it can work there, we know that it works anywhere. So this is where they group came, and then Avin also helped us in terms of doing that. NVIDIA Jetson also we have deployed it. We have also developed an Android communication, which we will use that, where you can simply load the image into the application, and then once you have loaded the application, then it will give you, what is the abnormal regions in terms of that. The first one it will be modeled. Right, so of course, this is available on GitHub. Those of you who are interested in go and do this. Now, those of you who are interested in a little bit more on what we have here. So there is a paper which was published in systems. And then later what we have done is that we have done little bit Comm a bit further, and then asked if it is truly point of care. What is considered point of care. So can we do the similar diagnosis using Amazon? Right. So again, there was a mini code net which we have developed, which is essentially uses the Amazon based point of care detection for COVID-19, and this was also published in the class, which I will say. I'm not presenting those results, but those are also very good. This is also a page article in the journal. So that is where I just found the first one. If there are few questions you can ask me. Otherwise, I'm getting the second one.
Yeah, we take a 5 minutes break after the question. Are there any questions you can ask?
There are questions.
Is more important, but medical accuracy.
Okay, so again, I can compare something like computer vision applications of Blackberry and others. Thousands of classes. Whereas here, for example, in this case, we are talking about 3 classes. We are talking about Blackberry. So now, this problem is not simpler than computer vision. So even though you are using a language network, where the language is much lesser, so you don't compromise on the accuracy, because the number of processes of parts. That's what we have to do. Right. So here the inference is bigger, but you look at the accuracies. Right? The best we are able to produce is what is known as nanoplastics. Right, so we are able to get the same balance. Because the problem itself is as I said, encoding 54 classes. Rather than computation, which is probably thousands of classes.
Think about data collection. Is data organization for sample is there?
Oh, that's a good question. It's not. Even though we can use the same operations, it is not. Because the reason is in the computer vision type of applications, what we call as computer vision type of applications, you have something to do with aspect ratio. That means that, for example, the same bottle, when I take it closer to the camera versus what happens in the far, is two different aspects. Right? So now this is what you are doing in terms of stretching operations. In the medical imaging, it doesn't happen. The protocol is fixed. That means that we make the same patient at the same level. Right? So we really don't do this kind of aspect ratios per se. Right? So that's why that implementation is not done. So the implementation itself is slightly different. We have deformation based augmentation. Deformation based augmentation. That again, augmentation itself is a big area. There are people who work only on augmentation.
Will it be different for positive classes and negative classes? Or
Not really. It was very different. Having said that, the number of positive cases are going to be less. Right? So, for example, let me just put it in this way. Right? So, WHO, which is World Health Organization, says that you require 3 beds per 1,000 people. This is the recommendation. That means more. There are 360 people around 1,000 of us. Correct? In that three, then you are talking, for example, let's say imagine that you are talking about COVID-19. Say this. So COVID-19 itself, out of 3, how many will happen? Right. So now in that again, we are talking about how much infection will be there. Right. So now you think about the amount of data available for positive ones. Negative classes, you might have thousands of data, right?
yeah.
The positive is getting 3,000. Right? Even assume that everybody is having those 3 are COVID-19, which is not at all. Right. So that means that the positive classes always is going to be a high skewed towards normal rather than abnormal. That's the problem we have. So that means that most of the accommodation you do is for the environment because they don't get the data. So even though ideally the accommodation should be the same, but most of the accommodation you are doing is for the environment.
Yeah, so just take 5 minutes break and we start the next one. Guys.
Small short break now.
Yeah, 5 minutes. Yeah.
You can access the refreshments at the back. Like you can just go through.
Yes, sir.
one question that we have is. I'll talk about it.
So what is the input television?
So, okay, that's a good question you asked. I think it was 5 hours.
The input you have taken to the process.
It's 5 hours. That's why I said we use AC.
Have you seen my slides?
देखा एक बार
Actually, I have to give a talk on in triple IT city.
ठीक है ये तो रिहर्सल हो गया रिहर्सल हो जाएगा Go slowly, then take 5 minutes break, then we come back again. It's not a continuous stretch.
Yeah.
Norway maximum 45 minutes. They will not sit more than, they do not have energy to sit more than 45 minutes. One stretch. You cannot inject more than 2-3 concepts.
Yeah. Even like I was surprised in IIT BHU they kept a lecture of 90 minutes. I was surprised how a person can deliver a lecture of 90 minutes.
I think I'll get started.
Yes.
So what I'm going to do in the next 40 minutes or so is to talk about what is called as INCAPS, the self-analyzed medical care, because I got another system such as I can fit it together and then give analogies little bit. But having said that, I'm also going to give a little bit of what is the futuristic ideas which are there in medical image analysis, which you could take up, which if I'm thinking about projects in this area, you could. So let me just go in, and again, I have a standard disclaimer which I received funding from, and these are the collaborators. So again, I know some of you have come late, so I'm going to just give a brief introduction to medical imaging, and then get into the autonomous healthcare a little bit. So let's get going on this. So I said initially that 90% of the medical imaging healthcare data is medical imaging. So in some sense, if at all you have to bring AI to healthcare, it has to be largely driven by medical imaging. That's for sure. And then I also said that you have these scanners which acquire the images. There are these radiologists or clinicians who are doing the interpretation. In between is where AI is. In between is where we would like to make this analysis efficient, faster, smoother. So now again, I also said that in terms of clinical needs, the funding medical imaging, faster, cheaper, less radiation, screening at the global level, and early detection are the keys. So that is what brings us to the autonomous healthcare. So I'm just going to take a intro, and then I'm sure a lot of you know this already, but I'm just going to refresh all the memories. So we have different levels of autonomous cars. So we call this as level 0, where there is no autonomous features itself. So the level 1 is, the cars can handle one task at a time, and automatic braking is one. ABS is one example where it will be able to do that, right? So ABS is one. The level 2 is that these have at least 2 automatic functions. Level 3 is that they can handle the dynamic driving task, but might still need a little bit of intervention. And those of you at least have seen XUV 700. The XUV 700 is level 3. To be able to do dynamic driving in some sense. And then you have these level 4, which are the cars are officially driverless in certain environments. Right? So for example, if we talk about Tesla is more like a level. So it is driverless, it doesn't require any intervention in certain environments, not in all the environments. Now again, level 5 is that it can operate without this. Currently, there is no level 5 that exists as of now. Right? And we have up to level 4 in the autonomous driving, right? So that is what's happening. Even though level 3 is more common, which is available across the globe. I'm not saying that level 4 is not common, but level 4 might be common in some of the countries. So again, if you look at the development of these autonomous cars itself, right? So 2010 is when people started saying that autonomous driving is possible. And 10 years down the line is where we are talking about having what I call as 10 million self-driving cars, or at least at the level 4 level. You are talking about having a millions, tens of millions of cars. So it took a decade for us to go from what I call it as concept to something being a reality. And it's not fully autonomous as well. So we are only talking about going in stepwise. So to go from something like level 2 was existing for a lot of the time, or at least level 1 was existing in 2010. To go from level 1 to level 4 We have taken 10 years. And of course, what is predicted is going from level 4 to level 5, which is completely autonomous. Right? So what is expected is that, at least to get 75%, it will take another 20 years. So I wanted to pay attention to this. What we are saying is level 1 to level 4, we are able to achieve in 1 decade. We are telling level 4 to level 5, we require 2 decades just to jump one level. Right? So there's a huge challenge to make it completely autonomous. So in terms of healthcare also, the same problem exists. So that means that you want to make certain tasks as autonomous as what we call it as self-driven. Probably you can do it, right? As machine driven, you can do it. But anything to go completely autonomous is not going to be something which is possible. So that's what brings us to this, right? So when we say autonomous healthcare, self-driving healthcare, what we are talking about is choosing the treatment plan. That is ultimate, right? When we are doing the screening, we are only doing one task. That's level 1, right? When we do diagnosis, probably that is level 2. Where we are talking about maybe grade 4, grade 5, right? It's doing those tasks. It's doing this, and then as well as staging. But to get to the level 4 itself is going to be extremely hard. Suppose that is where the money lies. Even for the autonomous class, getting to level 4 is not good enough still. Level 5 is what counts. So now where does it sit? In terms of the industry, so again, I can tell you the medical imaging world, there are only 4 major players. So that is GE, Philips, Siemens, CAM. These are the only 4 major players. Rest of them all doesn't really manufacture imaging equipment as a majority of us. They do some small ones, but not really major equipment manufacturers. Major equipment manufacturers have been GE, Siemens, Philips, and CAM. So now again, these are all what has come out to be the solutions, right? So I'm just going to concentrate on GE one, and Philips one, and Siemens one, and Canon one, right? Because I said that these are the most major manufacturers, even though there are other players which are. So Canon in November 2018 has included what is called a CT scan embedding AI solution for noise reduction. So when the noise comes in the CT image, they have included AI solution which will do the noise reduction. That might mean that might be it is doing some things, right? So again, Edison has opened a research platform to enable the deployment and development of AI where you can put your solutions, and then it will do these solutions. Philips said that it has a code AI model for screening and parameters. Again, the previous slide, I just would like to go back to the previous slide. What did I say about the screening? That is only doing one task. Right. So now this is in 2019, right? On October 2019, AI-based software assistant for chest CT to identify and measure results. Now this is more like measurement is comes under the diagnosis, right? So we are doing something more than the detection. So again, this is again level 2. Right? So this is what the major manufacturers have done so far, right? So far that means that what has happened until 2019 is only up to level 2. It's still not up to that. And again, so now, if at all I look at where do we think to go? Where do we think that, do we achieve really that treatment plan? What is required? So now again, I would say that, if you look at the medical imaging journey itself, the digitalization, which is the computerization of everything that is going on, has happened in 1990. 1993 onwards, there was a lot of standardization that has been done. For example, include like HL7, DICOM standards. These are all part of the standardization. So from 2000, the complicated analysis, which we are also called as image analysis, started, became a big thing. But the AI will play a role, right? So from 2018 onwards, the screening started, which is the low level that was talking about. And then we are talking about tools of diagnosis, which is currently high. Right? Most of the tools are in diagnosis. And then we got to get into the treatment part. So what is predicted is that beyond 2031, we can simply get the solutions which will do the treatment plan. Really before. Right? So that means that currently we are at level 2 equivalence in terms of parameters. And hopefully in another decade, we will reach to level 4. And because that's what we have observed with the autonomous vehicles, right? In 2010, it was level 2. 2020, it has become level 4. Right? In 2020, I am saying we are at level 2 in image analysis. Probably 2030, we might become level 4. But to get to level 5, which is completely self-driving healthcare, is what we want to do, autonomous healthcare. That might take another 2 decades from that. So by possible and entire possibly will all be there in the AI. But again, that is what is predicted is. So this is what brings us to where does the AI should really be used. So that is from the industry point of view, right? So when I say industry point of view, what is the commercial solution that exists? But if you go back and ask the radiologist, where should be the AI make a difference? Where is the AI making a difference? So that's an important question, right? From the user point of view, what do they want? Right? There are solutions that are coming up. But I'm saying, what is the user want? What does the user thinks currently where the AI is being used? I will not get into this, but I'll just say that one of the things which everybody thinks is that currently AI is doing is what is enhancing the image quality. Right? So we just talked about, for example, like Canon introducing AI solution to reduce the noise in the images of the CT, right? So that is enhancing the image quality. And what really ideally it should do is that it should identify new indication. That means that what is missed by me as a radiologist, it should also be able to do. That's a new indication, right? New findings. Ideally it should do. People think that it will happen in the next 5 years from now, but I don't think it will. But automatic is a part of the image analysis. So as image analysis, what we are talking about is those measurements. And currently, for example, like I just told you, that Siemens has that solution, measurement of the chest CT. It has already that solutions, right? And then we are talking about something like optimizing the workflow for overall productivity. So that then I told you that there are these image-based tasks we need to do as a part of the work. So that has to be optimized using the AI. And that triangle images to know most critical patients are critical images first to know. For example, when we look at HRCT, there are 140 images of the lung. Out of them, which one has that problem? If it is at 50, you start reading it from 1. You are going to take 50 images to come out. Can you start showing for 50? Saying that this is where AI thinks that this has that abnormality. So that we optimize the time of the clinician. Right? So that is what meant by triage, including the critical cases where we think there is a subcritical finding, that should also move up in terms of the number of patients as well. Patient. Of course, we are talking about as a clinical decision support system. Right? So that means that whatever decision you take as a radiologist, as a clinician, does AI also think that it is a good solution, or does AI give another same recommendation? Just augmenting that. So those are the easy cases. So now this comes back to those what radiologist wants. But currently there is a nice study which was done, again this is an independent field of radiology. Where does the AI stand in diagnostic radiology? This is a good paper for everybody to read, it's very non-technical, but it gives you glimpse of this. So I just wanted to point out that where does the AI solutions are getting deployed? Actually now North America has 41%, EU has 22%. Asia has a 90%, and then the rest of them have roughly the Now, in terms of imaging modalities, CT, MR, X-ray. Of course, X-ray, which is like just X-ray, radiography, and CT, almost they occupy 50% of the total. And then MR occupies some of the quarter of it. And then these are the image modalities that we discussed. And this is the most important part, right? So what are the solutions which are currently being done? What they have done. So the majority of them, 70% of them, do what is called as perception. The perception is enhancing the image quality. Right? So how does we see the images? So it's one of the tasks of the perception, improving the image quality. So now 70% of the AI solutions do improvement of the image quality. The reason, which is the quantification part, is only 70%. The processing, right, which we are talking about optimizing the workflows, in terms of the weight-based tasks, providing clinical decision support system. So those are all are part of the acquisitions. Those are all very good. So most of the solutions currently improve the perception of limits. That is enhancing the rich part. And that's where most of the algorithms are. The reasoning, yeah, there is a minimum, but there is only 70%. Okay. But more importantly, this is where what brings us to what are the things which have been found in this paper which are very relevant to us as people. The first thing is that there is something called FDA and CE here. These are all the regulatory bodies which will clear the applications for the clinical use. Out of all the solutions that exist, only 1/3 of them are what has been cleared by the FDA. And 95% of them are very specifically anatomical nature. So that means that they do only one, they do just X-ray, they do breast, they do brain. So they are very specific to anatomical nature, very task specific. And only 2% among perception and reasoning are prognosis related. So this is very, very important. So when we talk about treatment, the recommendation of the treatment based on what do they recommend? What is an optimal treatment for someone? That is a prognosis. That means that if you take this treatment, you will recover. Right? So that is a prognosis. But only 2% of the current solutions are prognosis related, right? If at all the AI is one which has to be futuristic in nature, which has to predict in time, right? Which has to forecast. Prognosis is the forecasting for the diagnosis. Only 2% of them are doing this. And only 3% of them are like this administration, scheduling and other things. Right? We are talking optimizing the workflows and other things. Only 3% of them are doing that administration, which is augmenting. Now, this is where the most critical part is. This is where we are all struggling, including me. Is that the effort and time that radiologists need to spend on launching and using these applications may outweigh their benefits. Very simply, if somebody has to use AI application, they have to download the data which is exists in their apps, right, and launch this application, load it into this application, get the result, and whatever result they get, they have to go back and import it into their system. Currently, it is not fully integrated. The AI application is working as a standard. Well, in the first talk when I talked about the Android app, that is not part of their integration. Right? So they have to have another app which they have to launch. They have to load the data, get the inference, get the output, and put it into the which that report might be different anymore. It might be a lot more easier for them to just see from that application which they are originally using and then make the finding. Right? So you think about maybe HRCT is a bad example because we have 120 pages. But you think about like just CT, just X-ray. Just X-ray is simple to image. Right? I will easily be able to see that image and then find out what is wrong. Rather than downloading that, putting into my application, and then getting the inference, taking that output, and then again putting back into my application. That might be more important than just making that just X-ray. So this is one of the biggest problems we have. And then there is something called as all the clinicians want to be bidirectional connection. What is bidirectional connection? Today, the way AI works is that you give it input, it gives you output. Right? But it's not asking me whether I can give any other input. For example, with just X-ray, can I mark on that? And then I want the AI to use that markings. Maybe I'm marking the suspicious region, right? Or maybe I'm just giving a tick, saying that look at this region more carefully, come back to the regions. Currently, that kind of interaction is not. Currently, it is given what you get out. That's what might be unidirectional. And then standardization of the data exchange, right? I just spoke about this launching this interoperability medical systems, right? So these both, the data itself has to be standardized. The interoperability has to be established. That is what makes the adoption of AI in radiology. Is that unless we have the standardization for the data exchange, how does the data bridge between the two systems? How can it transfer from here to that? Effortless. And then also talk about interoperability. Those are the key for the AI application. So if at all you are working in one of those areas, I would say that anything to do with bidirectional interaction is a big plus. So right now we don't have any such things. We don't have any such things. Anything to talk about standardization of the data exchange or interoperability? Again, that will include the adaptation. Now, this is what brings me to some of the other topics which we have not spoken about, but there is one something called as synthetic medical images. We talked about augmentation to a certain extent, right? But why not use the augmentation from another modality to this one? If I have a CT image, can I convert that into MR image? Can I synthesize MR image from CT? Or other way around, I have a MR image, can I synthesize CT image? Right? That is what is called a synthetic medical images. Can I generate those? There are certain things available. I'm not saying that there are no solutions there, but they are not really that good as we just seen. So the other one is reading the medical images. So we are talking about making the reports in automatic. Page to text is what we call this as. They're not that good. Because the reason is for example, if we look at chest CT, and if you ask, what are the findings? Findings means that what is wrong with the image? They are normalities. So chest CT alone has close to about 3,200 taxonomy findings. So 2D image, there are 3,200 findings, you can put it in there. Right? So that means that now your AI algorithm, even though I talked about 3 to 4 classes, if I have to make it as a text, not as a single image. If I have to make it as a text, then I'm going to find 3,200 findings. I have to map 3,200 findings. That's a problem we have. So image to text still a large level of problem. Then we talk about image reconstruction. We are talking about acquisition, which is there. But then from the raw data, cytogram data in the city world, time of flight data in the pet world, can we somehow use AI to reconstruct the images? And then there are imaging physics models. We talked about the expert knowledge about what to choose for the machine learning algorithm. That is based on physics. Can I learn that expert? Right? So that expert knowledge is what we want to generate using here. Can we develop those? And then this is the holy grail, right? So I call this as a holy grail. Right now, the way we are doing things, the data flow is we acquire the data. From the data, we do the image reconstruction. From the reconstructed images, we extract the features. Like, for example, in the COVID-19 case, the first talk that I spoke about, from the images, we were extracting those anomalies. Those are what we call it as these extraction or classification. And from there, we are choosing whether somebody should be admitted in ICU or not. That or somebody should be administered ICU. Those are the actions. Is all that powerful. Why to go about going on this? Why not go from data directly to the actions? Why to reconstruct it? Ultimately, your aim is, for example, in the COVID-19 case, what I showed, ultimately your job is to find out whether this candidate should be admitted in the ICU with oxygen or not. That is action. Why not go directly from the signing this? Why to reconstruct the images? Why to extract the features? From the features, why to say that this is action? Why not directly work on the raw data itself? And you don't require to look at the images because ultimately you are giving a recommendation. So why not do this? Right? So that's a big picture. And if you ask me, are there any people who is working on going directly from the raw data to the action? No, not me. I think we should be working on that. Because that will save a lot of the time, right? So that means that as soon as the data acquisition is over, I can take an action. Currently, reconstruction alone consumes about 4 to 5 hours. From reconstruction, again, feature extraction. Even the AI requires deployment. Right? So even extract the features, I require time. Right? So even the analytic is half a second, but somebody needs to move the data. And then it's going to take half a second. Why not go directly from the data to the action? Why to do all this? So now this is other thing which hopefully these slides are going to be distributed at least. That is
the data to action part, like are people working in the sense when people who learn part, do you know? Because it's a very similar problem that.
no, the reinforcement learning is a different paradigm. So where you are talking about giving incentives or giving some kind of
Sequential.
sequence. But I'm just talking about purely deep learning. See, the reason what we did COVID-19 infection was to answer the question, who is better suited candidate for the ICU? That's the answer we want to give. Right, so now the moment I have the data, can I say that how much is the infection rate?
Not like perform the action, just to learn.
You give the infection rate, automatically you find out. So now what we are doing is, from the sample lab data, we do a radar transfer, which is the linear transfer to get the images. And then again, from the images, we are doing the extraction of the pictures, which is the anomaly part. Based on the anomaly, what we have extracted, we are telling this much percentage of infection. Why not go to the sample data? Why not go about doing about all of these things? It's not, the effect of being is powerful. But if at all being is able to do that. So hopefully this is going to be distributed this slides. So there is something called as every 5 years. I think it could have happened this year. Every 5 years, the NIH, which is International Institute of Health, will conduct a big meeting about what should be the roadmap for the medical imaging. This is called as roadmap. It's done at the White House. So all the heads of the NIH will come together and then we'll put a vision document for the next 5 years. What we should bring the big impact. So in 2017 this has happened, in 2022 it's yet to happen. But there are 4 things they said it has to solve. And there are 4 big puzzles it has to solve in the next 5 years to come. We already spoke about data standardization. Today the data which is required is not standardized. So can we do data standardization? We are also talking about best practices in imaging. The protocols itself are very good. Can we bring the best protocols to this? Can we also use advanced computational machine learning? Can we also look at high value imaging? These are the 4 puzzles, which are the 4 pieces of the puzzle which has to solve this problem of the patient, right? So now again, there are different things which you are doing. Right? For example, in the interpretation, they are all talking about quantity, no longer quality. And we were talking about there are a lot of imaging surgical things are done which are unnecessary. So can we reduce that? Right. So for example, here we are talking about reduced need for further imaging or more time balance. If you have to do that, probably one of the solutions going with the from data directions. One of the solutions could be that. Now at every location, right? So now what I say is that every location there is a possibility for deployment. We just now spoke about new imaging reconstruction. Right? We are talking about decision support systems. Of course, this requires us to get into a lot of developments. So that might include data engineering, it might require concepts from data science, AI applications, and AI concepts. All of them have to be done. So not alone that medical imaging alone will be imaging, right? It has to come in general from the AI itself. So, and then we divide this into 4 parts. What at least I think, or what everybody in the field thinks, is that there are 4 major things that's going to change the way current AI is being applied in technology. So the first part is the way the current computing architecture is. So general purpose GPU has revolutionized the way we are able to train the deep learning methods. But there are more, right? So, but still, they have not really answered the questions of the privacy. Still, privacy is an issue. Because especially with the medical imaging data, which includes personal health records, privacy is still a concern when you are doing the computer architecture or general purpose GPU computing is what you are doing. So can we say that, can we develop these cloud platforms, which are really very much suitable, specialized for the medical imaging, addressing that? And especially the memory is also very much limited for a lot of the tasks. So that means that, we think that there is going to be generation of computing platforms which are catering to these medical images. As I said, 90% of the healthcare data is medical images. So if at all somebody has to develop AI solution, they have to develop for medical imaging first. And the rest will come later. And then the model architecture tailored to medical images. Right? So for example, lightweight signals are those architectures which are very specific to deployment, very specific to answer those things. The next one is the federated machine learning, right? So the privacy concern currently we are the ones which are not allowing the multi-institutional data to be collaborated and then used in the model because nobody would like to share their data and then put it all in one single server and then use it. So hopefully the predictive learning way we can take the model to all the locations and probably update the weights and then get one model out at the end of the day is the solution for it. And then hopefully that will address a lot of privacy issues, a lot of issues with the data integration part is going to go away with the fabric program. Right, so they are really very, very important for some of the rare diseases where we don't have enough data. So for example, like, you think about like sickle cell anemia. Sickle cell anemia is only present in countries like India. That also not in all the states. Most of the poor states have the sickle cell anemia. So now, for example, that's a rare disease. So if you have to develop the even the number of patients are going to be quite less. So now again, explainable AI. So I'm going to talk about explainable AI, but there is a trade-off between model performance and interpretability. So that we have to live with it. It has to be interpretable. Probably we have to compromise on performance. That is something which we can do. So there are still there are quite a bit of unexplored areas. In my view, even though I talked about new topics, but there are certain things which are not at all here. Right? For example, learning from the different laws. See, I told there are only 4 major manufacturers which manufacture silicon imaging. Each of the imaging equipment is expensive. Right? For example, if you buy a typical MR scan, or if you buy a CT scan, that will cost you anywhere between 2 crores to 5 crores. Right? This 2 crore machine, when it goes down, there is a lot of revenue that is lost. When the 2 crore machine is working properly, and that is, can you learn from that equipment loss? It generates a lot of loss. Using that loss, can I say that the machine is working properly or not? Can we say automated QC or QA? So right now the way we are doing is that we get the images and then we reconstruct it. After the reconstruction, we are telling, oh no, this image and postmortem. Then either the patient has to come back and then get the scan or we have to discard this data. But can we not say then and there that this image doesn't have any interface, or this acquisition is as proper quality? And that downtime prediction, right? So I told you about the spinal or something things. Can I say that when is the downtime? Can I predict the future? Can I do predictive maintenance? I'm developing 3D models, right? So right now we are not really doing 3D models. But most of our AI algorithms are revolves around 2D. But can I develop a 3D model which is like virtual reality type, which is synthesizing the 3D models? Can I do that? In terms of images. And under this real-time feedback of the image model. So that means that currently we assume most of the AI models will be coming out by IID, which is the distribution which we are assuming, which is not at all true. In reality, they are not IID. Right? So can I really give them feedback that this model which has been developed is this distribution? Right? When I get a new data, can I find out whether this is our distribution or inside the distribution? So now we don't have any tools. Right now we are not talking about how to find out that the data I have, which is a inference level, is within the distribution or out of the distribution. So now again, radiologics, the integrated diagnosis, right, where we are combining genomic data, radiology data, clinical history, everything together. So where we are using all the data which is present as some patient, including previous history, and then making a diagnosis, rather than just making the diagnosis purely with images, which is the current difference. If you look at the CT images, we are predicting how much infection. We are saying that this much percentage, right? So one thing which I have told you is, for example, somebody who had something like a infection, they also did. It is not like they did it, even though they didn't have an absence. Somebody who had 25% infection, right? They were not suited for ICU admission, but they were the ones who died. So there are two spectrums of things because we have taken things out of the context. So we have only looked at the infection rate from the images, but that alone is not the solution. Ideally, we should look at all of them. Now, again, there are some challenges for therapy. So I'm going to quickly wrap up for the AI. So one is that it's still a black box. Nobody knows what is going on inside, especially in the different parts. And then there is a problem of garbage in and garbage out. Right? So if you have a compromise on the quality of the data, then you have a compromise in terms of what solutions it gives. And there are not universal applicable large data set that is where fragmented learning probably can help. And fully integrated solutions are not possible. So currently most of them are very task specific. Either they need chest X-ray or they need HR center for home medical interaction. They are very much like that. Failure of earlier pulmonary detection systems, and they may get back. And then there is a fear of replacing the clinician. They all get feared of the clinician part. And then there is a compliance. So who gets penalized if the AI gets around? Do we blame the AI algorithm developer? Do we blame the quality of the data? So this is going to be the biggest struggle for us. And again, I have to tell you that, even though I spoke nice things about AI, there were many major failures for AI. And then this we have to openly acknowledge that this is where we are lacking. The first one is about what is called as national lung screening drive. This was done in the US. Where they were looking at pulmonary nodules in the chest CT. They were predicting that, what is the risk of you getting a lung cancer. We have the nodules, you can do it. It was working beautifully, 90% accuracy is very good. The moment they took that algorithm to Oxford University Hospital, the accuracy dropped. Across the US, they were looking at the moment I changed the domicile from US to UK, then the model itself was not working. Right? And then there is something called as adversarial attacks. We call this as a part of the, for example, chest X-ray. So the exposure is what gives you the noise in the R, what dictates the noise in the SNR of the images. So if we add a little small noise, the predictions were dropping to something like 15%. And the small noise is possible in the real time. In the real time, the small noise is coming because the exposure levels are not there. So these small noises were changing the way the AI predictions happen. Right? And then there's a big thing about WhatsApp for oncology and what's called from IBM Watson Temperature. So this was deployed in May clinic. And what they spent is $62 million. So roughly, if we think about it, we are talking about close to about 2,000 crores being deployed. And then, what has come is what the final conclusion. I just wanted to say that this was benched, but what they say is that the AI should be assessed in the same manner with the same rigor as the development of a new language screening test. Again, here AI was doing only screening job. It was not even doing a lot of the diagnosis. A lot of it was on the screening. Even there, it has failed. Even after spending all this money. So this is what brings us to what we call it as AI going with the trust. So the trust is ultimately has to be due with the explainability of data. People trust if the result can be explainable. People trust if the thing can be explained why this is behaving such a way. The problem we have is that we don't have that kind of thing. So the moment you start using the neural networks, the deep learning, what happens is that the learning information is very good. There's no need for daily domain explainability wise, because it's still a black box. And for example, if you are using anything like, I will say random forest, including SVRs, decision trees, probably the performance is not that great, but you will be able to explain better. So in some sense, maybe we have to draw somewhere in line, in somewhere here, and say that if you want explainability of the results, probably you better compromise. That's the typical way. So now again, I will just say that currently what I think of AI, this will be my personal opinion. So currently what I think is that they work as best as assistants and interns. They are not going to replace the clinician. So of course, the reason why you want to use AI is that you want to combine the human knowledge with the power of this. Yeah. Which will get 1 plus 1 greater than mathematical is not possible, but here it is possible. That you make these performance, both of them both, bigger. Pressure medicine and population health to tackle the complexity and expansions of the new data sources. You have a lot of new data sources. Every one of you who are using mobile phone, there is a new data that is coming, which is also related to your health. And everybody who is using wearable is getting tracking of physiological data. There is new data that is coming in. It's not in the controlled environment like in the hospital. Coming from everywhere. Can you do anything to the patient? Can you do population health? Of course, COVID-19 is one good example, right? The prevention is what everybody's doing. So that means that can we do early warnings? Can we do engagements? And give a personalized experience for the patient. So, right? So that's one of the things which everybody thinks we should do. Savings, can you reduce the labor cost? Right. Can we increase the consistency and value-based care? So that means that when you do this kind of things, AI-based ones, we might be able to do this very well. And again, I will not say that, one of the things which I would like to quote here is that there are three things I would like to quote, is that the greatest danger of AI is that we all conclude that saying that we understand. Really, we don't understand. It's still a black box. So if you ask me why does the CNN work, I'm not. Right, so I may be able to explain it slightly better, but if you ask me hardly, why does the CNN is able to make this prediction? We don't understand. Why does it do it? Right? So why does the deep learning network works? Nobody's why does only 1 works? Why not? It doesn't work with 20 years. Yeah, I mean, answer those questions. Right? And again, the healthcare at least is too much of the human notion. So AI will not do it. So AI will not be able to take the healthcare of the community supply much at all. But most important thing is that the radiologist or the clinician who use AI are the ones who are going to be very, very efficient. They are the ones who are going to replace the radiologists who use the AI. So that's why I'm going to stop. Thank you very much. If there are any questions, I'm ready. Sure.
Radio integrated diagnosis, combined clinical history and like everything.
Correct.
So that means to medical imaging or it can be a trial.
So medical imaging itself is a feature in the integrated care. But so if you think about it, we are building a feature back. So images will go as one feature, right? Genomics will go as one feature, right? So now the clinics will go as another feature. Right? Even for example, genomics can go as one feature. Right now, what we are doing is that we are using imaging at one, and we are making the prediction.
My question is clinical is already a good value. Whether it is good or one, it should be good. Can it be converted to trials so that it is the performance of the model?
Yes, right now there is a lot of people use it, but the problem is we are not using all the patient history. We are only using for the context what is the patient history. Right? So for example, today you got the imaging. We are looking at the temperature of today. Let's imagine the temperature is one feature. We are looking at blood pressure of today. You are looking at ECG of today. Then you are inputting this as an organization. Ideally, what I should do is that I should look at what has been the patient history from the birth to now, and then use that information to make the diagnosis. We are not doing it because part of the reason is that the health record system is not standardized. That's why data standardization becomes very, very important.
Well, then it has a feature.
Yes, that's the feature work with.
One real-time data for the other distribution. The domain acquisitions in here, because the price being the distribution.
Is what?
Domain adaptation.
No, not really.
I mean, like, we try to identify from which domains is coming from, right?
Correct. But domain adaptation is a step which you apply.
Yes.
Before even you apply the AI model, right? So very simply saying that, for example, let's say that you take the example of X-ray CT. So do you make everything go through the domain adaptation? No, right? Now what you are doing is some of the data which has come from different scanner is the one probably you do domain adaptation. So that means that you have some prior which has come out of the distribution. Further, you are able to do, which I agree. But I am saying, even within the scanner, there is a lot of variability. For example, I'm just giving in this example. Somebody who is 24-year-old, somebody who is 80-year-old is going to have entirely different organ details. So ideally, we should do domain adaptation for everybody. Because ideally, it should be what we call it as test and adaptation for every single patient. Because every single patient is different. But we are not doing it. Right? Or if it is not doing it, then we got to find out which are the ones which are clearly out of the distribution, which you can call as outliers. And then do the domain adaptation. Do we have any tool which will say that this data is from out of the domain? No. Right? But why not? Because we have the training data. Training data is something which is present. Can I now come with a statistical measure of what is the distribution of that training data? Now, when the new data comes, Maybe I have some performance metric, or maybe I have some evaluation metric which says that if that evaluation metric is within this, then it is within the distribution. Anything which is not in this is out of the distribution. Then I have to do the domain adaptation. We are not doing it. We don't have to.
Yeah.
Okay, thank you so much for.
Thank you so much, sir, for your talk. Actually, it has covered all problem statements in the healthcare domain. In a 1.5 hours, 1.5 hour talk, it is not easy to cover every problem which are relevant to the healthcare. So we are all having a very good time with you, sir, today for 1.5 hour nearly, and we have got so much of knowledge from your talk today. Thank you so much for your time. And I request Linga Reddy, sir, to give you a small token of gratitude. Just a small moment from IIT.
Thank you. Thank you. Slides.
Slides.
వైఫై ఎడు రూమ్ రావట్లేదా ఎడు రూమ్ రావట్లేదండి అసలు వైఫై ఉందా ఇక్కడ లేదా ఆ బిల్డింగ్లో వచ్చేది మంచిగా అది రావట్లేదు కదా మీకు వస్తుందా ఇప్పుడు వస్తుంది ఇదా ఓపెన్ నెట్వర్క్ ఉంది కానీ IITH@computer మీ స్మాల్ లెటర్స్
ITS capitals. And we need you. And do you have any traveling base? Okay.
Should I put?
No need, sir. If you have, you can, or else you can just sign here.
That one we will arrange later also. The travel one. Prepare
Sign.
Okay, take this and take this clear pen.
Okay, thank you.
So I welcome you people to for the second talk of today. So I feel honored to introduce Omji Pandey. He's received his BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lucknow, India in 2008. The MTech degree in Digital Communications from ABV, Indian Institute of Information Technology and Management, Gwalior, and India in 2013, and the PhD degree from Department of Electrical Engineering, IIT Kanpur, India in 2019. He worked as a postdoctoral fellow with the Communication Theories Research Group, Department of Electrical and Computer Engineering, University of Saskatchewan and Saskatchewan, SK, Canada. Currently, he is working as an assistant professor with the Department of Electronics Engineering, IIT BHU, Varanasi, India. His research interests include the signal processing for wireless networks with a specific focus on robust sensor node, localization and tracking over wireless ad hoc networks. He also works on related areas such as low latency data transmission, data aggregation, and distributed detection and estimation in wireless sensor networks. He is a regular reviewer for various reputed journals of IEEE, including the IEEE Transactions of Vehicular Technology, IEEE Access, IEEE Internet of Things Journal, and the IEEE Transactions on Communication. So he's taking over this So we kindly request you to take over the session.
Yes, just a moment, I'm just.
Is full screen or?
Actually, one transition is going here. No, you can. So, first of all, thank you very much, Professor Lincoln, for giving me the opportunity to present this work in this particular workshop. So, the topic of the presentation is small world models for IoT applications. So, there are three important words you can see here. First one is the small world. Second one is models, and third one is IoT applications. So what basically we have done, we are introducing small world phenomena that we will see that what is a small world phenomenon. You know various models, and we are introducing in the wireless networks to improve the performance of Internet of Things or even cyber physical systems. So to understand this, first we will go through to understand that what is cyber physical systems and Internet of Things. So this from left bottom, this is an illustration of deployment of wireless sensor network, where there are various sensors and they are sensing the physical world phenomena in a limited radio range region. And they are transferring the data in a cooperative manner to the sync node, and sync node is connected to internet, and end user is fetching the information, whatever the information has been monitored by these sensors. So there are several questions that why it is monitoring in only over a certain limited geographical region, and why we are transferring the data in a cooperative manner rather than transferring the data directly to the sync node. So there are certain challenges associated with wireless networks, such as how to maximize the network lifetime. Because if we are talking about wireless sensor network, then we are going to deploy the sensor nodes over a geographical area where we can extend the life of the sensor nodes for more than 2-3 years. So we want that the network should operate for years. And that's what we are going to transfer the data in a cooperative manner. We are transmitting the data with a limited data rate. So this is why I am showing this, because it is going to work. This particular entire system is going to work as a backbone for Internet of Things and cyber physical systems. If you are talking about Internet of Things, then always sensing phenomena will take place, and that will happen through a wireless sensor network. So an illustration that how this in the real world, how this deployment will look like, that is illustrated at the right bottom. And this middle one is showing that how Internet of how wireless sensor network is going to work as a backbone for Internet of Things, and how the cyber physical system is going to be developed with the help of WSN and Internet of Things. So here you can see that even for wireless sensor network, even we are doing fixed sensing, we are doing mobile sensing. And all the sensing information will be transmitted, the data will be transmitted to the cyber world, and cyber world will perform certain computations, and it will back transmit the actions to control the physical world phenomena. So when we are going to integrate this actuation, or you can say action, into this Internet of Things, then it is going to be called as cyber physical system. So what from beginning, what we have seen that what is wireless sensor network, what is its real deployment, how it is going to work as a backbone for Internet of Things and cyber physical systems. So this entire slide is showing the introduction of wireless sensor network, Internet of Things and cyber physical systems. I hope it is clear to you. Now, as I told you that wireless sensor network is going to work as a backbone for Internet of Things, we should know that what is the architecture of wireless sensor network. So essentially it is having three layers: bottom layer, middleware layer and top layer, that is application layer. And bottom layer used to communicate with the middleware layer using operating system and communication protocols. And middleware layer will communicate with the application layer with application abstraction module. So what we have done within the middle layer, there are certain challenges associated with WSS service module. For example, if you will explore that what are the challenges associated with wireless sensor network or wireless network, node localization, time synchronization, low latency data transfer, energy balancing phenomena, data gathering, data aggregation. There are several issues which are associated with wireless service module within middleware layer of wireless sensor network that we have addressed, and we have addressed through a small word form. So in the beginning, you have seen the title as small word models for IoT applications. So what basically we are doing, we are introducing this small world phenomena in a wireless sensor network to address those challenges. So what is the motivation? Because we in current stage itself, we can see there are various applications which are driven through CPS and IoT systems. And the applications you can see from here to so many applications: smart grids, mining, industry 4.0, smart agriculture, logistics and supply chain, smart transport. There are plenty of applications which are based on wireless sensor network, Internet of Things, and cyber physical systems. So this is the motivation that why we are going to introduce this small world phenomena in a wireless sensor network. Now, as our key topic is small world models. Because if you are able to understand that what is wireless sensor network, what is Internet of Things, what is cyber physical systems, and we have gone through the architecture of wireless sensor network, we have understood that yes, middleware layer is having certain challenges, and we are addressing those challenges with the help of small world phenomenon. Then the most important question is that what is a small world phenomenon, and how I'm introducing this small world phenomenon in wireless sensor network. So, small world phenomena was firstly observed in the year 1967 by Stanley Milgram, and he performed certain mail delivery kind of experiment, and he concluded that in this world, two randomly selected persons are not more than 5 to 6 steps to each other. So he performed mail delivery kind experiment, and he started from Bob, a person in Nebraska, and he transferred the letter to Lasan, a person in Massachusetts. And he concluded using that particular experiment that in large population, randomly selected source and destination, the average path length between these two randomly selected persons are not going to be more than 5 to 6 steps. And this is known as the small world phenomena in this social context. After that, in the year 1998, there were two persons, Duncan Watts and Stephen Estogate. They observed this phenomena inside graph. So what they have done, they have taken a regular graph, which is well structured graph, and they performed certain rewiring in that particular graph. Means they have removed certain wires. So, for example, you can see that this wire is removed, and they have added this wire is removed and that is connected here. In similar fashion, another link they have created here. So what is happening? By doing this rewiring, they are getting certain phenomena observed in this particular graph, which will be helpful in the context of graph. But further, if you are going to do this particular rewiring, then the graph is going to be converted to a random graph, which is not very much useful. So at present, you can just understand that if you are doing this rewiring with a less or moderate level of probability of rewiring, you are obtaining a small word graph, and if this probability of rewiring is going to increase to a high value, then you are getting a random graph. And if the probability of rewiring is 0, then we are having a regular graph. So what we are doing, we are moving from a regular graph to random graph. So now the important question is, what is the characteristics? On what basis we can say that this particular graph is a small word graph, or a regular graph, or a random graph? So the two essential parameters are average path length, which are shown on this vertical axis, and clustering coefficient. So if I'm talking about a regular graph, about this particular graph, if I'm talking about this graph, then the average path length and average clustering coefficient, both values are high in this particular region. And if I am doing certain rewiring in the graph, then I am getting a small word graph which is having high average clustering coefficient and low average path length. And if I am doing more rewiring, then I am obtaining a random graph which is having low average path length and low average clustering coefficient. So, there are certain advantages. If I'm talking about low average path length, and I just want to let you understand that what is the advantage of low average path length and high average clustering coefficient. You can understand in this fashion that if you are in the first slide I told you.
I think you missed to introduce the definitions of the clustering coefficient and the path length. Oh, okay.
So now average path length, what we have observed that a small word phenomena is having low average path length. So the low average path length means if you are having a network and you want to transfer the data from one node to another node, you are taking less number of hops to transfer the data. That is called as path length. And when you are computing this path length over the entire network for all possible combination of node pairs, then that is known as average path length. And clustering coefficient that we want higher, clustering coefficient is going to tell you that what is the clusterness of a node in the network. And clusterness is going to be defined by that if node A is connected to node B, C, and D, then how node B, C, and D are connected to each other, that is going to define the clustering coefficient. Now, in the context of social connectivity, I just want to let you understand that what is the benefit of high average clustering coefficient. Suppose in the society you are well connected and you are facing any problem, then you can share your problem with your friends and they can help you. They can help you. Okay. So on this similar line, if I am talking about wireless sensor network or wireless network, when I am transferring the data from one node to another node, I want to transfer the data in optimal number of hops. Why? Because if I'm transferring the data through multiple hops, At each hop, there will be various kind of delays. For example, queuing delay, processing delay, propagation delay. So if you are able to avoid the, uh, if you are able to reduce the number of hops, obviously you are avoiding those delays. And if you are able to maintain highly misclustering coefficient, it means you will be able to make an energy balancing phenomenon. For example, if the certain node is experiencing that it is having less residual energy, less remaining energy, the node can transfer this information to other nodes to whom the node is connected, and they will be the responsible guys to further forward the data of that particular sensor node. So, with the help of this particular high average clustering coefficient and low average clustering and low average pathway, we are able to address certain challenges of wireless sensor network. So, this has been observed by Duncan Watt and Introverse in the year 1998 in the context of graph. And in the context of wireless sensor network, there was a guy, Gaurav Sharma. He is from IIT Delhi. He observed this phenomenon in wireless sensor network, but he made some wired connection. Through physical wires, he reduced the number of hops. Further, many researchers came forward and they understood that yes, if wirelessly we can connect the node pairs over a long distance, then it would be helpful. So here you can see that we are having, these are the wireless transceivers. And some wireless transceivers are connected over a long, using a long wireless link. And over this particular, you can say it's sensor network, that is wireless sensor network, we are creating certain number of long range wireless links, and we are introducing this small word phenomenon. This is a small word model developed by us at IIT Kanpur. We have developed this small word wireless sensor network using simulated test bed and over real field sensor node deployment node. So this first row, this is corresponding to simulated test bed, and this second row is corresponding to real field sensor node deployment. This is conventional wireless sensor network, and this is small word wireless sensor network. This is conventional wireless sensor network developed using real field sensor nodes where we are using NI modes. And this is a small word wireless sensor network developed using real field sensor node development. So what basically we are doing here, we are using data mills, and we have done partitioning of this particular network into 4 regions, and we are keeping the mule at the center of each region, and the mules are responsible guys who will create the long range links within their region. And by doing so, we are able to observe that we are able to reduce the average path length, we are able to maintain high average cluster coefficient. So for simulated test bed, we have taken the area as 400 cross 400, and we have used 300 sensor nodes. Then what will be the radio range of individual sensor node? I think 11 or 12 meter we have taken. And for real field sensor node deployment, we have used 33 cross 29 meter square area, and we have used 80 sensor nodes here. So this is an illustration of a small world wireless sensor network developed by us. And what is the motivation? So in the beginning phase of my PhD, I was looking for some problems, and I gone through some of the research articles which are listed below, and I observed that yes, there are various advantages if we are able to successfully introduce this small world phenomena in the wireless sensor network. We are getting reduced localization error. We are able to improve the time synchronization. We are able to reduce the data transmission delay. We are able to reduce the network overhead and many other challenges. For example, we can make the energy balancing phenomena. We can increase the network lifetime. We can reduce the energy consumption of individual nodes. But what I observed that yes, this is the motivation, like because we are addressing several challenges associated with wireless sensor network. But the methodology what they are proposing, that is not optimal or suboptimal. That is conventional approach and that is not very efficient. So we have proposed some novel algorithms. We have introduced some small world phenomena using some novel framework, and we are able to address the same problem in more effectiveness. So what are the existing methods? So as I told you that in case of graphs, they have done the revamping. They have removed the link from one place and they have connected to over a longer distance. But if you will look for wireless sensor network, then how to introduce, because that is different from the graph theory, because you have to do real-time implementation. So for that, you can use either utilizing wired links between node pairs. But if you will say that somebody that I am going to introduce wired link within wireless sensor network, anybody will laugh. Okay. So this is not possible, and even if you will look for the physical constraints, physical wire constraints for various applications. For example, if you are going to do flood monitoring, you are going to do battlefield surveillance, you cannot go and deploy this physical wires, right, in the wireless sensor network. So this method is not suitable. Yeah, for some of the applications you can do, but as wireless sensor network is essentially developed for the applications which are unattended or hostile area. So this particular wired link introduction is not suitable in most of the applications. Now the second important aspect is introduction of heterogeneous sensor, which are called as H nodes. So, like what you will do, you are having sensor nodes and you are mounting multiple radios on the sensor node. And you, whenever you want to increase the radio range transmission for a longer distance, you can activate other radio and you can create long range link. But there are certain constraints with heterogeneous sensor nodes also. For example, if you are going to mount multiple radios over a sensor node, you are going to increase the cost of the sensor node. You are going to increase the hardware complexity of the sensor node. The sensor node, individual sensor node will consume more power. So there are certain various challenges associated with H nodes also. After that, the third aspect is using data maps, which are mobile nodes. So if you are using mobile nodes, what I have done already in one of my work. So what is going to happen? The mobile node will move and it will create a long range links that will cause a longer delay for data transmission, because you will say that you have to transmit the data over a longer distance. The robot or whatever the mule you are using, that will move and it will transfer the data. So this particular application is going to increase the data transmission delay. So yes.
Can you explain further regarding I didn't understand the previous figure in which you showed there are different, clusters or something, and you are in your work, this one, yes. So you are saying that like you are introducing mule concept over here, wherein for some, I'm assuming those are sensors, all are sensors.
Yes.
And we are putting a mobile device, like a cell phone, basically mobile user equipment.
A robot we have used.
Robot that is not a part of sensor, basically.
Exactly.
not a part of sensor, but we are based on the density of the sensors, we are placing the mule.
Yes, yes.
Okay, and we are providing internet or.
Yes, we are telling that mule will be responsible person who will make the connection between two nodes to introduce this small node phenomenon.
Okay.
Okay, so that like if you want to in this particular region, if this particular node wants to transfer the data to this particular node, you will use this particular mule, and it will be a responsible guy who will try to connect, who will connect these two sensor nodes. Okay. So the third method.
So that's basically mobile gateway.
Mobile. So the fourth aspect of introduction of a small world phenomena is beamforming, which is very popular, and currently I am working on this also using collaborative beamforming. So the beamforming means like rather than omnidirectional transmission, you will mount an antenna array over the sensor nodes and you will try to do the beamforming. So rather than wasting the sensor nodes energy over the region which are not helpful for the introduction of a small word characteristics, you are going to mount antenna array and the sensor nodes will transmit the data over the long distance and they will introduce this small word phenomenon in the network. But with this, if I'm talking about multiple input MIMO system where you are going to mount an antenna array over the sensor node, you are going to further increase the hardware complexity because you have to mount an antenna array over the sensor nodes, and that is not helpful. Hardware complexity you are going to increase of the sensor node. That is a problem. So what currently I am working on collaborative beamforming, where the individual sensor nodes, what you are deploying, they itself form a group and they will do collaborative beamforming. And with the help of collaborative beamforming, you are going to create long range links within the network and you are introducing this as small word phenomenon. Okay. So the methods, if you want to explore, there are this. This is hybrid, a case of hybrid sensor networks, where he has used wired and wireless both cases to introduce this small word phenomenon. So in the literature, there are various papers which are available and they are using only these approaches. But if you will explore, you will find very less paper which are introducing these small word characteristics using the concept of beamforming. Now, what are the research contributions made by us? So, we have addressed the problem of node localization, and we have addressed this data gathering and low latency data transfer, energy balancing phenomena, and fault resilient distributed detection and estimation over small node wireless sensor network using beamforming. So, these are the research articles. Apart from these research articles, I have also published other research articles, but they are because they are in the initial phase when I started working on this particular problem, they were published. So they are listed over here. So if you will go through my profile, you will find other papers also, which are introducing this small node phenomena in a wireless sensor network using various concepts. So now I'm going to start this first work where you can understand this. We are going to address the problem of sensor node localization using heterogeneous sensor node. We are using heterogeneous sensor nodes. We are assuming that the sensor nodes are mounted with multiple radios. So what is the problem formulation? We are trying to reduce the average path length of the network, and we are trying to minimize the number of links need to be introduced in the network. And we are putting a constraint as over the number of long links which will be introduced in the network, and we are putting a constraint over a reduction of average path length if we are doing it in an iterative manner. Because if you are going to introduce a single link in the network topology will change. So what we have done, we have introduced long range links at a single time also, and we have introduced this long range links in an iterative fashion also. Iterative fashion means you will introduce one long range link in the network, and after that, because you have to compute the shortest path through which the data will be transferred, and when you are going to introduce a single long range link, the complete routing will be changed. So when you will compute again the average path length, it will be lesser in comparison to the previous case. So what we are doing, because we have to introduce this small word characteristics, we are putting a constraint on clustering coefficient and average path length both. So what is our ultimate goal? We are trying to reduce the average path length maximum, and we are trying to maintain average clustering coefficient as high as possible. So what we are doing, we are normalizing the average clustering coefficient and average path length both. And when the reduction in the average clustering coefficient of the network is more than the reduction in average path length, we are stopping. We are not introducing the long range links. So these conditions, in one condition, if average clustering coefficient is less than the reduction in average path length is less than the reduction in average reduction in average clustering coefficient is less than reduction in average path length, then we will try to introduce the long range links. And once we are getting more reduction in average clustering coefficient compared to reduction in average path length. And why we are basically doing this normalization of the parameters? Because you cannot compare kilogram with meter, right? So you have to normalize, you have to bring the on the same platform so that you can compare the average path length and average clustering coefficient. And according to that, you are introducing long range links till you will get the maximal difference between average path length and average clustering coefficient. And that is giving you optimal number of long range links introduction into wireless sensor network. So this I have just explained that what are the parameters in this problem formulation I have used. So this is the LR and NR is corresponding to random network, which we are considering that the average clustering coefficient and average path length corresponding to random network is almost equal to 0. We are considering that the conventional wireless sensor network is having maximum ACC and maximum APA. And this HK, LK, IM, JM is giving you the average path length at kth time instant, where HK minus 1 is giving you the average path length at k minus 1th time instant. Because you have to take the difference of the average path length between two discrete time instant values.
Probably the subscript you can give the notation varies. For example, k is going over time and there are m and n, right?
Yeah.
So a brief.
Yeah. And what we are doing, we are looking for the link with this optimal link is obtained, which link is giving us the maximum reduction in average path length. Now the question is, yeah, this work has been done and has been published, but still there are various open challenges. Like when you will look for this maximal reduction and you are having suppose 500 sensor node, searching of the link which will give you maximal reduction is related to time complexity. That is not addressed in this particular work. If you, in later stage, I published another paper that is published in NCC 2021. There I worked on the time complexity also, how we will reduce the time complexity. So in this particular work, I have not addressed the issue of time complexity. I have just told that yes, I am able to successfully search the link which will give me optimal average path length reduction. I am not bothered about the time complexity, that how much time I will be needed to search that particular node. So this is the problem formulation, what we have seen, and this is an illustration. This one is when I am introducing this long range links in a iterative fashion, and this is when I am introducing the long range links at a single time instant. So you can see that here I have done numbering. This is first, this is second, this is third, this is fourth, this is fifth, this is sixth. So I have introduced total 6 number of long range links in the network. And as I am going to introduce this first long range link, the entire routing process, or you can say the routing methodology, will be changed in the network. However, if you are doing at a single time instant, then you are not worried. You will say that I have to introduce this 6 number of long range links so that I will get the maximum reduction in average path length. But this will not be effective if I will compare to this particular method. But the disadvantage is, in this case, I will get improved time complexity. My time complexity will be less, but in this case, my time complexity will be more, because at each time, again and again, over all possible combination of node pairs, I have to search the optimal long range link. Okay.
Basically, you have to do here the 6 times, there you do only 1 time.
Yes.
Okay.
Yes. So this is the real field sensor node deployment, which I have already shown you in one figure just before in previous slides. So in this particular real field sensor node deployment, I have just implemented the algorithm proposed by me, and this is the conventional wireless sensor network, and this is the small mode wireless sensor network, when I'm introducing this long range links in a iterative fashion. So what are the area and this black dots of the sensor node, all those things are mentioned.
Yeah, here one question is, when you are doing iterative manner, from first step to second step, are you going in a way that you are actually minimizing the average path length, or you are just randomly going?
No. We are minimizing. We are looking for maximal reduction of average
okay.
interesting of.
Yes. Okay.
So that's what I'm telling, that if you will go for this over a large geographical region with large set of nodes, the time complexity will be very high.
Yeah, because you have to search.
Yes,
Okay.
we have to search. So this is the performance comparison with iterative manner and non-iterative manner. So what I am doing with in a iterative manner, that I have written as a iterative APN, iterative SSC, and which one is I am doing at a single time, that is non-iterative. So you can see that I am getting, in case of a iterative method, when I am using iterative method, I am getting better reduction in APL. While in case of non-iterative, the APL reduction is not that much when compared to iterative approach. And ACC, I am getting almost same. So what from this particular slide we can conclude? We can conclude that if we are able to introduce this long range links in a iterative fashion, then we are getting better small word characteristics in the network. We are getting better small word characteristics over the wireless sensor network. But the trade-off is the time complexity for the development of a small word characteristics will be more, that I have not shown yet. So this is the performance.
What is the time complexity of that one order of the time complexity for searching?
Hours.
They're going in hours.
Hours. Then sometime it is going to 16, 17 hours.
When you are basically selecting all together, all wrong line, not the iterative manner, non-iterative manner.
That is very fast.
That's very fast.
That is fast.
Because
what you are doing, what the entire process, like if you are going to introduce 6 long range links,
yeah.
so at a single time, how much time you require to search a single link, the same process for non-iterative method is going to happen for all the 6 links. So almost you can say if you are going to introduce 6 long-range links, then the time complexity will be almost 5 times, 4-5 times in comparison to non-iterative approach.
Yeah. Is there an optimal method?
Yeah, so that is still we are looking for. We are looking for some machine learning framework to
So that you can
we can propose
optimally
in less time.
Yeah.
So this is the performance evaluation, and we have obtained the results over 3 different data sets: simulated data set, Intel lab data set, and real field sensor node deployment. And basically, we are using RSS model for the measurement of the distance between node pairs. So one is model-based approach, RSS model-based approach, and other one is model-free approach. So model-free approach, I have taken a reference from this particular paper, that how to measure the distance in model-free localization method for sensor network with sparse anchors. So I have, for RSS measurement, I have taken the RSS base, like if you know the RSS measurement model, log normal sorting and frisk transmission model, they are the RSS measurement models. So for RSS, I have taken model base and model free, and the 3 data sets corresponding to 3 data sets, that is the real field sensor node deployment and Intel lab data set, Intel Berkeley lab data set, and simulated data set. So we are getting 6 lines for the performance. So as we are introducing the long range links, we can see that how the localization error is going to vary, how the bandwidth power consumption is going to be there, how how much bandwidth requirement is going to vary, and how many number of anchors are going to need to be required to localize the sensor node. Because if you have worked on the localization process, we are using certain anchor nodes to localize the blind nodes. So we want minimal number of anchor nodes required for the localization of the sensor nodes available in the network. So we can see that the localization performance is going to improve as we are going to introduce the long range links in the network. As we are obtaining these small word characteristics, we are getting better performance in the context of localization accuracy. But the trade-off is we are going to consume more power and the bandwidth requirement is also going to increase. But another advantage is we are getting reduced number of anchors required for the localization of the entire network. So we are getting the advantage in terms of localization performance. We are getting better performance in terms of number of anchors required. But there is always a trade-off. If you are getting somewhere some advantage, always you will get some disadvantages also. The disadvantages are in the context of power consumption and bandwidth requirement, but that is very slightly increased in comparison to the conventional network. Okay. So the same results I have illustrated here in the form of radar chart. So this one is corresponding to simulated test bed. So this particular row, this first row is corresponding to conventional wireless sensor network, and this row is corresponding to a small world wireless sensor network. This column is corresponding to simulated test bed. This is corresponding to Intel lab dataset. I have used one dataset. If you will type on Google Intel lab WSN dataset, you will get that particular dataset. That is having 54 sensor nodes deployed over an area of 59 cross something. I'm not able to exactly recall that particular dimension. But if you will type on Google Intel Lab WSN dataset, you will get that particular dataset. So this is corresponding to Intel Lab dataset, and this is corresponding to real field sensor node deployment, that what we have done at IIT Kanpur. So what we can observe from this radar chart, that we are getting lesser area covered by, in the case of a small world wireless sensor network, when we are comparing to conventional wireless sensor network. And most importantly, if we will see that localization error performance, that is going to be reduced. However, the power consumption and bandwidth requirement will be increased. And we have also illustrated that what are the values of APL and ACC in case of these networks. Okay, so we have obtained the performance over 3 different data sets, and we are getting better performance in case of all 3. So we have also done these grammar or lower bound on localization parameters, that error variance performance, that how the grammar or lower bound analysis need to be performed on the localization performance. So that is going to tell you the error variance performance, that how the lower bound on the error variance, how it is going to be performed. And we are taking the location parameters as X and Y parameter. And we are writing the Fisher information matrix, which is given in equation 5. And because this sees the covariance matrix, which does not depend on phi, means it is independent to the location parameters of the sensor nodes. So this whole expression is gone. Now you have to just compute the value of d mu phi by d phi. We have computed that this, and we have got the Fisher information matrix, and the Kramer lower bound will be the if you want to compute the Kramer lower bound from this Fisher information matrix, this is given in equation number 8, and we have plotted this. We got this particular performance, that in case of conventional wireless sensor network, we are getting more error variance in comparison to a small mode wireless sensor network. And we have taken the difference of these two from conventional wireless sensor network to small mode wireless sensor network. We are getting positive values, and we have taken the ratio which is always less than 1. So this is an illustration on Kramer or lower bound on error variance performance. Why we are getting on the corners we are getting high value? Because of the poor measurement of RSS value at the corners. The sensor nodes which are located at the corners, we are getting poor value. So this was the first problem on sensor node localization. Now this is the second problem which I have addressed, that is low latency and energy balance data transmission over a small world wireless sensor network, and I have introduced this small world characteristics in a cognitive manner. So how I am introducing this small world phenomena, that we will understand later. First, we will understand this problem formulation, that what is this particular problem formulation. So what is this Fij and Cij that represents the Fij is representing the amount of data which are going to be transferred between node pair I and J, and Cij is the cost corresponding to the link over which we are transferring the data. So our objective function is to minimize the product of cost and amount of data transferred over the network. And we are minimizing with respect to the parameters F and C, and we are using certain constraints. And the constraints are, if the distance between two node pairs is above a certain threshold which is denoted as R max, then the amount of data transmitted over that particular node pair I and J will be equal to 0. And we are also putting a constraint on data flow constraint. Data balancing phenomena means whatever the amount of data has been transferred, means outgoing data from a node will be equal to incoming data on that particular node. And the third constraint is on the cost again, that if the link, the radio range between two node pairs is going to below the threshold of the long range links, then always if the amount of data is greater than 0, the cost will be also greater than 0. So this is
What is that The second constraint physically mean,
Basically means like if you are having a sensor node, there should be always a balance of data transfer. So if a node is generating some of the packets which are going to be transferred,
it has same number.
Exactly.
Okay.
So it is a data flow balancing constraint. Actually.
Mm-hmm. It has to transmit and receive the same amount.
Exactly.
Oh, fine, fine.
So this is the problem formulation for low latency and energy balanced data transmission. And to address this particular problem, what we have done here, this black dots are indicating the sensor nodes, and this blue links, this first black links are the conventional links, which are having limited radio range. On the basis of that, you have developed this particular network. Now, this blue links and red links are the long range links introduced in the network at time instant tau 1 and tau 2. You can also see in this, there will be various green links, magenta links at time instant T3, T4 and T5. Means what we are doing, we are introducing certain number of long range links in the network at various time instant so that we will get the optimal small node characteristics in the network. And how we are going to identify that which node, for example, I have taken this node and I have connected to sync, this node I have connected to sync. On what basis I should select the sensor node which will be connected to this sync node? That for that we have used a probabilistic model. Yes.
Here, why are you not doing only one time? Why are you doing the multiple time instances?
Okay, so what is going to happen here? That is an important question. That is a good question. Actually, what is happening? Suppose I will not introduce a red one. I will just introduce this blue one. So what is going to happen? The life of this sensor node, I think this is 8 or 3. I'm not clearly able to read. I think 3. Its life will be very tough because he will be the responsible person again and again to transfer the data over the long distance. So what will happen? Once it will transfer the data over a long distance, 1 time, 2 times, 3 times, at 4th or 5th time it is going to die because it will be responsible to transfer data of many nodes. Okay.
Got it.
So what is going to happen? For that, I have used this particular probabilistic model. Depending on that, what is the residual energy? I have kept here residual energy. Residual energy, clustering coefficient, node between centrality, node degree, node geographical distance, and half count distance. I have taken these 6 parameters and I have assigned probability to each and individual sensor node in the network. That what is the probability at present the node is having so that I can connect that particular node to a longer distance. If the node is having high probability, it means it is having high residual energy, high clustering coefficient, high half count distance. And so I have kept certain parameters in numerator, I have kept certain parameters in denominator also. So why I have kept certain parameters in numerator and certain parameters in denominator, that also depends on that how effective, how I am able to improve the performance of the network. So if the node is having high residual energy, obviously you want to assign high probability. But if the node is having high betweenness and centrality, you want to assign less probability. Why? Because that will be the node which will be responsible to transfer the data of many other nodes. So if you are going to create the long range links from the node which is having high degree or high geographical distance, then you are going to consume more power. Our goal is to reduce the average path length, not the geographical distance. So if the node is located at very large distance, suppose, so you want to give low probability because if you will see the energy consumption model of wireless sensor network, you will realize that it is going to, the sensor node is going to consume the power at the rate of t square or d to the power of 4, depending on the distance over which it is transferring the data. And that is very popular model. The paper is having more than 20,000 citations. Okay, so what is happening here? If the distance is going to cross that particular threshold, and you are going to connect that particular node to a long distance, obviously the power consumption level will be of the order of d power 4. The network, that particular node is going to die out very fast. You are not able to balance the energy consumption phenomena across the network. So that is the reason you can go through this particular paper. You can read, I have written that why I have taken this parameter in numerator, all these three parameters in numerator, and why I have taken these three parameters in denominator. And ultimately, we are getting a probability which is assigned to individual sensor node. And depending on us that how many long range links you want to introduce, and that depends on that what value of small word characteristics you want to introduce in the network.
Have you considered the amount of data and amount of time?
Data and time.
How much data that node will be transferring and how much time it will be transferring?
Okay, so yeah, so that result I will show you.
Okay.
Result I will show you.
Fine.
That I will show you. So actually, so with the help of this probabilistic model, and I have normalized also all the, with the help of this equation 6, I have normalized all the parameters, and I have assigned the probability, and I have introduced this small word characteristics. Now this is the illustration of conventional wireless sensor network. This is the small word wireless sensor network at a particular iteration. This is the Leach protocol, which is very popular protocol. If you will see in wireless sensor network, you will type Leach protocol. This is a low adaptive protocol for data transfer, where they are going to do the clustering of the sensor node. Like that is going to use K-means clustering actually. K-means clustering, that is on the basis of distance. They are going to cluster the sensor nodes, and these are the cluster heads which will be responsible for transferring the data to the same node. So I have compared my approach with Leach protocol also. I have compared my approach with conventional wireless sensor network also, which is doing multi-hop data routing. I have done I have evaluated the performance over direct data transmission also. And I have compared the performance by my own method also. And the most important point is this paper, this Leach protocol is very popular, and I'm getting performance better than this Leach protocol using small word phenomenon. So this is the illustration over a real field sensor node deployment. I have also evaluated the performance over simulated test bed. So this is the performance. If you will see the performance, this one is corresponding to simulated test bed. This one is corresponding to real field sensor node deployment. And we are getting better performance in the context of data transmission delay when I'm going to compare with the conventional multi-hop data routing. But my performance in the context of data transmission delay is not better than protocol and direct data transmission, because they are faster, they are transferring the data very quickly. And on the same line, on similar lines, I'm also getting the same result in our real field sensor node deployment also. But the advantage comes in terms of network lifetime. When I'm going to compare the network lifetime performance, the iterations, I'm getting more number of iterations for which the network is going to survive when I'm going to compare with direct, leach, or multi-hop data routing protocol. Okay. So the same results I'm getting for both simulated and real field sensor node deployment, and this is the number of iterations, that how many iterations the network is going to survive. So in terms of iterations, not in terms of time, and we are assuming that this many number of bits is going to be generated. For example, you can assume that if that sensor node is going to transfer 1 byte, means 8 bit, and all the sensor nodes are going to generate the same amount of data at each iteration of the data transmission. Okay, so that we have done, and we have got this particular results, and this paper is getting my work is getting good citations, because we are getting better performance in comparison to Leach protocol when we are going to compare the performance in the context of network lifetime maximization.
So actually, I wanted to ask this question: how it was different from K-means clustering from the beginning, actually. So, like as you said, sir, like K-means is getting better performance when in converting for the data latency. But as per your algorithm, we are actually trying to increase the length.
Yeah.
So, like, can't we do the same, like, getting energy efficient in K-means clustering? So, I didn't understand why we are going for this instead of K-means clustering when our job is a bit simpler, like what it is the exact difference.
So the exact difference is like what you are doing in case of K-means clustering. K-means clustering is going to tell you that you will supply that how many number of clusters you want to make. You will give as input that I want to make 6 clusters. Depending on the geographical location, the clusters will be formed. And from that particular cluster, there will be again a competition that who will work as a cluster head. So depending on that, how much residual energy the sensor, which one is having maximum residual energy, that will be opted as a cluster head. And after further, many researchers, they have proposed modified Leach protocol also, where they are rotating the cluster head when the residual energy of the sensor node is going to below certain threshold. Okay, so that is a approach of clustering. You can say our approach is focusing on. So how my approach is different from your what you are asking, that Leach protocol. If you will look for the Leach protocol, you are kind of going towards random network, because you will not get better average clustering coefficient. You will get reduced average path length, because as you are able to form the clusters, the individual cluster is able to transfer the data to sync node very fast, because the average path length is reduced. But what are the modified versions of the Leach are proposed? The modified Leach version of the Leach protocol is saying that you are going to rotate the cluster head within the cluster. But how many options you are having? You are having limited number of options, because within the cluster head, within the cluster, you are having 10 or 12 number of sensors. But if you are going to adopt small word phenomena, you are having full flexibility and you can rotate. Same thing I am also doing, but over across the entire network. You are getting?
So, and the cost of delay.
Yeah, the cost of delay.
Okay. So this is one of the work I have done during my postdoctoral work. So this is this is the collaborative beam forming, and this is the beam forming from the individual sensor node, you can see. So what we are doing, we are considering that this particular sensor node, individual sensor node, is mounted with antenna having, and we are going to do the beam forming. So their beam forming is MBDL beam forming also you can perform LCMB beam forming also. The advantage of LCMB beam forming is you will generate the side lobes, while in case of MBDL you will not be able to generate this particular side lobes. You will be able to generate only a single lobe, which will be the male lobe. So we have proposed this particular, we have used this particular LCMB beam forming rather than FVDR beam forming. And we are introducing this small mode characteristics using this LCMB beam forming. And we have seen the performance that if we are able to successfully implement this small mode phenomena in this particular wireless sensor network, we are getting better distributed detection and estimation performance over wireless sensor network. So this, if we want to extend this particular work, we can look for another applications. But in that particular work, I have explored this distributed detection and estimation performance. Right now, I'm working on this particular collaborative beamforming, where you can see that the challenges associated with this particular mining beamforming is you are going to increase this hardware complexity of the individual sensor node. Here, you are treating a group of sensor node as the antenna, and they will do the beamforming. So you are not going to increase the hardware complexity of the sensor node, even you are able to introduce this small node characteristics. So currently I'm working on this collaborative beamforming problem. This is, nobody has worked on this. So I'm working on it.
The same frequency resource will be used for
Yes,
all.
same.
So will it be overutilization of resources?
Overutilization of the resources you cannot say, because ultimately you, if suppose you are going to work on this IEEE 115.4 protocol, that is JP protocol, you are going to use 2.4 to 2.485 gigahertz, right? So when you are generating the data from individual sensor nodes, they all are transferring the data. All are transferring in that particular frequency band. So here the same phenomena is going to take place. What the phenomena is going to take place here, then the same phenomena is also going to take place here. Only you are going to do the transmission in certain order. So the same thing what is happening over a conventional wireless sensor network transmission, the same transmission is going to take place over here. Only you are just giving a say that how the transmission will take place. Okay, so you are able to successfully, if you are able to introduce this small node phenomena using collaborative beamforming. So far, we have not got any result. We are working on it, but I have a great belief that we will get better performance. Now, the very important question is where we are stuck right now. That which set of sensor node I should use for the collaborative beamforming, how many sensor nodes I should use the beamforming, towards which direction I should do the beamforming. And we are also struggling right now for the measurement that suppose what is happening actually, we are trying to identify that suppose I had kept the beam length till here. Okay, till here I'm going to stop myself. Now the question is, till where I should go? And if I want to go beyond this, then what will be the optimal number of sensor nodes? And if not even optimal number of sensor nodes, what will be their locations? So it is a very complex problem. I am struggling in this particular problem.
One small question, sir. At any given time instant, if all the sensors are transmitting the same information through the same frequency.
Yes. Okay. So this is an open problem. You can also work on it.
But what about the lifetime of the nodes when you do the beamforming? Is it not going to be reduced? No.
No. Because if you are we are just utilizing. If the sensor node is transmitting in omnidirectional with the same power it is transmitting, but that is not helpful for us. If we are doing beamforming with the same amount of power, transmission power, we are able to transmit over a longer distance. That is reducing the average path length, and that is giving us advantage in some other way.
Yes.
So even I'm also exploring this energy harvesting concept in here, because sometimes you will realize that some of the nodes are depleting their energy very fast. And some of the nodes which are lying at some location, they are having too much residual energy, but they are not transferring the, you can say, data. At some of the locations you will realize. So to make energy balancing phenomena or to increase the network lifetime, I can utilize the energy of those sensor nodes and I can harvest to those sensor nodes which are depleting their energy very fast. And even if you will look for the applications of unmanned aerial vehicle, that I will also tell you. At some of the applications, you will realize that even if you are wasting our 100 watt of power, and we are able to transmit 1 watt even, that is better. That is better because some of the applications will be like rescue operations. You can recharge your drone again and again. You can call back your drone and again you can charge it. But to transfer the data to the, you can say the sensor node which is located at a battlefield, that is more valuable. So that is dependent. Because why I am telling you? Because if you will if you will go through the literature, you will realize that the RF-based energy harvesting is going to consume more and more power. So we are going to waste more power in comparison to transferring the power. You will transfer 100 watt, you will even not get 1 watt. But that is application dependent. So energy harvesting also I'm working in this on similar lines, that if I'm able to propose a better algorithm which will do the energy harvesting in wireless sensor network using a small world concept. So this is the motivation behind distributed detection and estimation, and we are getting better performance. You can say convergence rate, if you will see for distributed detection and estimation, you are getting better performance in the context of convergence rate and mean square error and error variance. So as you can see that if we are in the regular network, we are not getting better performance. Even if we are in the random network, we are not getting better performance. But we are getting better performance in the small world. And that paper is published in IEEE Transactions on Signal Processing. This group, they have published and they have obtained this particular result. So this is not my result, this is their result. I'm showing you that we are getting better performance in the context of distributed detection and estimation. That was the motivation behind working on distributed detection and estimation using LCMB beamforming. So they have used some some different method towards introduction of a small world characteristics, but they are getting better performance. And I have addressed this issue using beamforming concept. So this is, so far we have talked about this wireless sensor network, where the sensor nodes are having limited radio range capability. Now, if you will see IoT and cyber physical systems, then they are right now getting help from LoRa communication, long range communication. So LoRa is giving you flexibility that you can transfer the data over a longer distance. But if you will look for the current demand of data generated by the sensor nodes, then every device is generating huge amount of data. Even if you will talk about medical applications, that sensors are generating every second huge amount of data. So if you will use that, then the device will die out fast, even you are using LoRa communication. So for that, what we have proposed a reinforcement learning framework in low power wide area network, where we are transferring the data in a multi-hop fashion. And currently we are working on this small world based LP WAN. So this paper is not related to small world phenomenon. This paper is only, this particular work what I have done, that is only related to reinforcement learning. And now we are developing a model where we are utilizing this reinforcement learning framework to introduce this small world characteristics in the network. So we have taken certain state of individual sensor node, and we have taken certain action and we got certain reward. So action is that I have to transfer the data to which particular distance. Should I transfer the data directly to the gateway, or should I transfer the data to the very nearby sensor node, or to a sensor node which is located at moderate distance from that particular sensor node? So what we have done, we have used this reinforcement learning framework, and we have tried to maximize the cumulative reward. Cumulative reward, and reward we are measuring in terms of that how much power the sensor node are going to consume, how much bandwidth we are going to take for the data transfer. So various parameters we have taken, considered, and we have developed a function, and we are trying to maximize the reward using this particular framework. Now, as part of a small world model, we are developing. I have already told that we are going to propose some algorithm through which we will reinforcement learning framework through which we will introduce this small world phenomena in this particular network, and we will improve the network performance in the context of low power variability. Okay, so this is the work where the sensor nodes are static. But if you will see the situation like healthcare monitoring, if you are talking, then if a patient is wearing some of the sensor nodes, it is not guaranteed that he will be static in the environmental condition. He will be mobile also. So if you are going to work in a mobile scenario, then the topology of the network is going to change. For example, if the network is having at time instant this particular topology, at time instant T2 this particular topology, at time T3 this particular topology, then it would be difficult to identify that because because of the change of location, you will not be able to identify that which sensor node I should transfer the data. So here you can see this node 24 is located here, node 24 is at time instant T2 is coming here, and time instant T3 is also again static. That is like from T2 and T3, it is almost static. But in case of T1 and T2, it is going to change its location. So when the sensor nodes are mobile in the environmental condition, then selection of the sensor nodes from one sensor node to another sensor node that to whom I should transfer the data, it is quite difficult, and that we are also addressing in the context of time varying network. We are proposing some reinforcement learning framework, and we are addressing the problem in the context of a small world also, a small world phenomena also, and in the conventional framework also. Now this is socially aware millimeter wave networks using 3D beamforming. So here we are basically using the concept of 3D beamforming, where rather than only doing this azimuthal beamforming, we are doing elevation beamforming as well. So what is the advantage of this? Here we are using socially aware. Socially aware means like always using the social relationship index factor, we can identify that the devices which will be in a cluster, because usually we can identify that this particular person is going to be with whom, and most of the time he is visiting to which particular location. Okay, so we are using social relationship index factor, and we are using 3D beamforming concept, and we are transferring the data in a more efficient way over the network. And as a part of future work, we are also introducing this small world characteristics, because they are socially aware sensor nodes. We are also working on it, that how we can introduce this small world characteristics further, that from the access point, after getting the data over the clusters, how efficiently we are able to transfer the data over this particular geographical network to further reduce the latency, improve the network lifetime, to make the energy balancing phenomena. So this is also an open problem. I'm also currently working on it. So this is a UAV assisted small world LoRa communication solution that we have already submitted in IoT journal. So here we are having drones, and when we started working on it, we are having the problem that how to introduce this small world characteristics in this. If we are using a single layer UAV, we can work on multi-layer UAV also. But if you are working on single layer, because UAV will change its location with varying time, and it would be difficult for us to identify that which UAV pair need to be connected at different time instants, so that we will maintain a optimal small word characteristics in this particular network. And after that, we will transfer the data from this particular layer of UAV to the ground station. So when we were working, we were struggling a lot that how we will identify this, that UAVs are changing their location and how to identify this, that which UAV pair need to be connected. And we have proposed a reinforcement learning framework where we are able to successfully implement this small word phenomena in UAV network, and we are able to introduce this optimal small word characteristics in the network, and we are able to improve the performance of this particular UAV assisted small word LoRa communication. So this is what I told you in the previous slide, that this is a single layer UAV. Now, if we are going to work on multi-layer UAV, so multi-layer UAV means like if you are going to deploy different layers of UAV, then how to, because now earlier the problem was on in 2 dimension. This is the problem of 2 dimension, and you are in a particular height. The layer is situated at a particular height, and on this particular height only you have to maintain this small word characteristics. But suppose this problem is going to be in 3 dimension, and you are having multiple layers, and you have to maintain optimal small word characteristics in this particular multi-layer UAV, that is more critical problem. And we are designing basically for backhaul infrastructure development. And here we currently I have started working on it, but we have not yet got the solution. And we are introducing this small word characteristics in this multi-layer UAV assisted optical communications. So this is the total work. So I just want to tell you that this small word phenomena is very attractive, and many research groups are working currently on it, and they are having various scopes. Even if you will talk about low power wide area network, even you will talk about UAV assisted LoRa communication, UAV assisted optical wireless communications. Only the challenge is because like you are going to work with a time varying network. In the case of static network, introduction of small word characteristics is simple. But in case of time varying network, it is quite complex because the devices are going to change the location. And currently, we are working on some machine learning framework so that we can identify in minimal time that which node pair, mobile node pair need to be connected so that we can maintain optimal small word characteristics at varying time instants. And if you are able to do so, you can address many challenges of wireless sensor network or low power wide area network or UAV assisted wireless networks.
Small question.
Yeah.
Actually, I was looking at this, but I didn't understand like what, I mean, like, basically now we are trying to find the link maybe. We have a communication protocol. I'm not sure, like I've asked, like in wired, I think this router, like, if there are switches and router, how we are routing the data from, through multiple routers or switches. And we have seen the cadence clustering algorithm also. Like we have different algorithms, to find this thing. What does the small world phenomena exactly mean? Like, which one shall we say that yes, this is small world? Like, is it like the as per your problem statement, you're trying to what do you say, energy efficient one? You said
No, clustering. There's a definition defined in the first slide, right?
yes, but I mean that is somewhat similar to like that comes under this also, right?
Yeah, you are telling that this particular where I should stop.
Yes, exactly. Where I can say that is small world.
So basically, what is happening? Getting exactly value, that at what value of SCC and APL I should stop, that is very difficult. You cannot identify that, you cannot tell that this should be the APL and this should be the ACC. This particular is a reason. In a particular reason, like what you can do in another work, what I have done. I am in an iterative manner, I am going to introduce this long range links in the network. So as you are going to introduce this long range links, obviously average path length is going to reduce. Average clustering coefficient is also going to, it will initially will be maintained high, but after a certain stage, it will reduce drastically. So what you can put, you can say that I am looking for the number of long range links in the network, which will give me maximal difference between APL and ACC. You are getting? So if you will say that I'm saying that this is also, this point is also a small word reason.
The distance is.
But this distance is lesser in comparison to this distance, right? So wherever you are getting maximal difference between APL and ACC, that is the optimal small word characteristics. Okay. But if you are able to somehow in this particular region, that is also a small word region. Okay.
Thank you, sir.
Thank you so much, sir, for your time and wonderful talk. I request Professor Vedalek sir to give you a small token of gratitude.
Yeah.
Just
Thank you, sir.
Thank you.
So we have a lunch break, approximately 1 hour. I think we got delayed a little bit, but it's fine. So we take 1 hour to eat, and we will come back approximately one hour